and we also develop partnerships with international collaborators with the goal of sort of mutual projects that benefit both our organization and yours, as well as the building. So one of the ways we do that is, of course, Stratfor, which is building capacity for institutions, knowledge and action. Also have student programs, have funding that we provide for our office to support students to travel internationally and complete internships and dissertation research. So one thing that we did want to share was that there are 6 departments, and each of those departments has both master's and doctoral level students. Departments span from biostatistics, epidemiology, environmental sciences, health education, nutritional sciences, and health industry. And so students from all of those backgrounds may be interested in actually traveling and projects where you could benefit from the additional support of the students for developing your scope of work, gathering data, working with data. So I have some business cards here. Now, if you'd like to take one at any point, always help questions about student programs as well as our office. So students are available in the summer to travel, so that would be an however, there could be times where a student or project to collaborate. So I just wanted to please reach out. Outside this thing in terms of the internships, yeah, office in general.
No, I would like to touch on the primary sort of. I think for your needs, the student internship probably is the best solution that you provide. The one most important thing is that it's actually free of cost to your institution. So this is funded entirely to the Office of Global Public Health. So the student kind of airfare, accommodation, then so it's funded by the public health. The only sort of expectation we have is that someone from your hosting acts as the local mentor along with the that children. So while the student is here, and we have sent students past, when was that? About 3 years past. I see 10 weeks, 10 weeks, right? 8 to 10 weeks in summer. And I think so if you have projects where use some help there on the design, or actually it doesn't have to be because my students have that but as Kiran mentioned, we have students from epidemiology, from health behavior, from nutrition, them diversity. So on programs, spread the word to other faculty. So a lot of departments were doing research. So they definitely benefit. So yeah, thanks.
Okay, so do we have people joining on Zoom?
Yes,
are there people? Okay. Okay, so we did not have any microphone here, did we?
Oh, yesterday we didn't want.
I don't know if you can hear me fine, but if you so the while this is the microphone is being set up. Again, I don't have, okay, I'll just leave it here in case. In case you cannot hear me, just let me know, I'll use the microphone. So the plan today is to talk about categorical data analysis. Now, once again, categorical data analysis is a vast field, and it's a very widely used field in biostatistics, because all of you are kind of trying to understand a disease process. What we are going to present today is almost like the tip of the iceberg. And we are going to focus on binary outcomes. So before I get into that, let me just make sure that we all are sort of on the same page. Yesterday we talked about fundamental issues in statistical inference. Talked about, estimation, we talked about point estimate, confidence intervals, we talked about sampling variability, which is a very, very important sort of concept. And then we talked about test of hypothesis testing. So in a natural sequence, what would come next is a discussion of linear regression. Because linear regression is sort of, I don't know if I mentioned, it's kind of the mother and father of all regression models. And it is the bread and butter. And the reason why linear regression is very important to understand linear regression first is because a lot of the concepts and a lot of the ideas for hypothesis testing, confidence interval, all of that inferential ideas carry over from linear regression to all the other frameworks for regression. For example, logistic regression, which we'll talk about today. The other thing is, in linear regression, oftentimes the primary interest might be on a certain exposure variable, or let's say on an intervention, but you want to adjust for other things in the model, right? You may, for example, the LDL BMI example that we were talking about yesterday. So you want to understand if there is an association between LDL and BMI. But in the process, you want to adjust for age, gender, dietary patterns, and all the sort of extra variables that could impact LDL also. This is what statisticians call adjusted analysis or accounting for covariates, or more kind of like technically, we say that you need to account for confounding, adjust for confounding. So we touched a little bit on randomized clinical trials versus observational studies. And Dr. Sinha yesterday mentioned that most of your studies here are observational studies, which is where all these issues about confounding, missing data, confounding by indication, all these sorts of like really difficult to tease out things happen. In randomized control trials, you have ways to balance the treatment versus the control group in terms of other things that could affect the outcome. But in observational studies, you don't. It is what it is. So when we talk about yes.
We should be coming back to p-value again today.
No.
So can I ask one question?
Sure.
Yesterday, because I did ask because of the time constraint. So p-value, if it is question on p-value, one is that if a lower p-value, does it mean that there's a stronger correlation? What I mean is that suppose one p-value is 0.01 and another p-value is 0.0001. So does that mean that there is a stronger correlation, or it means that there is a saving?
No, a p-value of 0.0001 would mean that it is highly significant. The association is highly significant. But you don't order the p-values. Like if you are thinking about ordering the p-values in terms of, so another p-value of 0.03, you want to make the both are significant.
So
But
can I keep, like when I say writing a review or something like that, can I say that that p-value was, so that study was more significant than the others?
well, people qualitatively say that, but you really cannot compare p-values across. I mean, you can compare p-values across studies, but you cannot use p-values to compare across variables. That's the point that I'm trying to make. Say age. Age has a p-value of 0.0001, but gender has a p-value of 0.01.
Same variable. For example, I'm trying to find out whether
But different studies.
A drug and B drug
Yeah.
is useful in a condition.
Yeah.
And say A drug, they have said that useful p value is 0.01, and for B drug, they have said useful p value is 0.0001.
No, what do you mean by A drug, B drug? Like, is there a control group?
For example, in the say I'm making it up. Say in the condition like tuberculosis,
Yeah.
I find that there is a drug A and there is a drug B.
Yeah.
One study has said that drug A is significant.
Yeah.
It improves the outcome by p value 0.01.
Yeah.
And another study has said that drug B is significant outcome and p value is 0.0001. So can I say that the drug A is better, drug B is better?
No,
than
you
A is
cannot.
better?
You cannot. Because you can say that, this study showed that drug B is highly significantly different than control. And another study said that there is, sort of marginal difference, significance in comparing drug A to the control in another study. You cannot use p-value to compare and say that drug B is,
Because what I understood was that if it is significant, it is significant.
It is
And the number doesn't.
No, you shouldn't do the ordering based on p-values. So what can you say? Like this is what I was coming at, that you can, that's why the point estimate is the strength of association or the effect size that we talked about. So the effect size is what? The difference between drug B versus the control, adjusted, standardized for the variation. So the effect size is important. You have to report the effect size.
And that's where the confidence interval will also be.
Yes,
Because
yes.
if it's one study, the confidence interval is very wide, and the
Exactly. But you really cannot compare with p-values. And the other thing I have to say is that when you're comparing across studies, this comes back to design. The populations may be different, right? So you don't know underlying what are the things they adjusted for. So it will never be an apples to apples comparison.
And the other question related to p-value was that I was told somewhere that if the p-value is less than 0.01, then you shouldn't be giving the numbers. Like sometimes we give p-value 0.004 or 0.006. It's based just a p-value less than 0.01.
No, I mean that's more of a convention thing. So most journals say report it up to 3 places of decimal. But that's more of a convention thing. Like again, if it's less than 0.01, so think about what p-value really means. P-value is saying if it's 0.01, it's saying there is only a 1% chance of finding, observing results like this, given the null hypothesis is true, under the null hypothesis being true. So only a 1% chance means basically it's quite unlikely that this could happen if the null hypothesis is true. So you end up rejecting. So p-value is better than a binary reject, do not reject decision, right? Because it doesn't really tell you like how likely or how unlikely. Whereas a 0.001 is saying it's a 1/1000 chance, like even a much smaller chance that you would find something like this under the null hypothesis. So from that respect, it gives us it's an evidence, quantitative evidence about how likely or how unlikely your result is under the null hypothesis.
So,
But you should
advise,
never-
like, when we are writing up, should we put the exact p-value?
I usually quote the exact p-value. But once again, I'm saying this question is more of a journal editorial sort of decision rather than a statistical decision. Your job is you report the p-value in like 3 places of decimal. Some journals have the convention that, you know, if it's less than 0.0001, in fact, people report it as 0. But that's more of a journal convention. Okay, anything else? Okay, so now what I was saying is, so we in linear regression we talk about all this confounding, then we talk about what is called effect modification or interaction. How many people have heard the term effect modification? Okay, so effect modification is a term in epidemiology, and for statisticians, basically what that means is we call it interaction. So what is interaction? Let me mention that. So interaction is, let's say again take the BMI LDL example. Suppose gender modifies the association between BMI and LDL. What does gender modifies means? So what that means is how BMI affects LDL varies between males and females. Epidemiologists will call that effect modification by gender. Biostatisticians will call it that there is an interaction between BMI and gender. So in other words, remember the straight line that we were sitting? So the slope of BMI with LDL will be different for males versus. That's what interaction means. Why am I talking all of this before even going to the first slide? That's because when, as a natural sequence, after what we talked about yesterday, we should have talked about linear regression. Because linear regression builds all those frameworks formally for a continuous outcome variable y. And then you carry forward those concepts into all other regression frameworks like logistic regression, Cox proportional hazards, regression models for censored or survival data, and all that stuff. Since we didn't do that part in the middle, and again, I totally understand why we chose to talk about categorical data, because that's the kind of data you encounter more often rather than a continuous outcome. You are like, disease, no disease, cancer, no cancer. So we will kind of skip. We are skipping that whole, and actually in PGI, the 2 days we talked about linear regression, we talked about model selection. How do you select? Like you have tons of variables, let's say you have 50 variables or so. How do you decide which variables to put in your model? How do you use prediction? Like how do you predict for a future child, like what their outcome would be based on the model that you have built? So that's a big chunk that we are at this point skipping. But what I will try to do is when we talk about categorical data, I'm going to try and refer back every now and then to kind of customize the lecture in the framework of a binary outcome. But if you feel like there is some sort of a hole in the understanding because we have skipped a lot of stuff, then please ask. And maybe we won't be able to do justice this time, but we'll do it some other time. Okay? So I just wanted to make sure that we all understand there's a big part that we kind of skipped, but let's try and see whether we can refer back. Okay, so with that, today's topic, categorical data analysis, and I decided we are going to keep it again to the simplest form, binary data, because that's exactly what you encounter most. What are binary variables? What summaries can we use to describe binary variables? Are these proportions, odds? What is odds? What measures of association can we give between a binary predictor and a binary outcome? What is the relationship between testing the difference in two proportions and testing for an odds ratio? You all have read about odds ratio in the literature, but maybe you are sort of not clear about the interpretation of odds ratio. So we will talk about those. So in linear regression, what is the measure of association? It's the slope. First, you look at correlation coefficient, but then when you go into the multivariable framework where you have lots and lots of variables in your model, then it's the slope or the coefficient associated with each variable. So for a linear regression model with outcome as LDL, and then the predictors or covariates as BMI, age, gender, diet, smoking, you would look at the beta coefficients associated with each of BMI, age, gender, smoking, diet. Okay? So in linear regression, it's the beta coefficients. It's the traditionally what we call the slopes. In categorical data or in the situation where the outcome is binary, what is the equivalence of that slope coefficient? And that's what we are going to try and understand today. Okay? So binary outcome variables, we will focus on outcomes that have a yes or no response only. For example, does the person have a disease or not? Did an employee quit within 6 months? Does this person present with some chronic liver disease or not? So more generally than yes or no, we can talk about a 1 or 0. So 1 would denote yes and no would denote 0. Okay, and this is a very important point to keep in mind, because how you code the yes and no in your software does have an impact on what you are getting. Again, as I said, for any software, garbage in, garbage out. I'm not saying this if you made an error in the coding here that you would get garbage, but you would have to change your interpretation. So you have to be very careful of how you are coding. Generally, the yes is coded as a 1 and the no is coded as a 0. Because with that coding, you will get the probability of having disease. If you did the other way around, if you coded yes as a 0 and 1 as a no, then you would get the probability of not having the disease. Okay, so that's something to keep in mind. So these types of variables are called binary variables. Descriptions of binary variables, typically this gives the percentage of time the answer is yes. The percentage approximates the true probability of yes in the population where the study sample came from. For example, in the WGCS data that we kind of like referred yesterday, what is the proportion of participants who experience a CHD event? In the pre-course survey that we did and collected, thank you all for returning the surveys. Like we got a sense of the composition of the audience, and we are also asked about software. So not many people, understandably, have used statistical software. 1 or 2 that said yes, they said SPSS. So looks like there is some familiarity with SPSS. So generally for us statisticians, our software of choice is R or SAS, but in our graduate program in biostatistics, R is the most widely used. Why? Because firstly, R is free R is a very strong programming language. So if you are developing your own methods, writing your own code, it gives you that flexibility. But R also has a steep learning curve. So it's not a very easy program to learn. SPSS, on the other hand, is more user friendly. So I understand some people may have used SPSS. So what I did is I kind of customized to show you some outputs from SPSS. Once again, this workshop is not to teach how to do things in SPSS. So what you are it's more about like concepts, interpretation. But what you see here as outputs, we will take those and we will try together to interpret what that. Okay, so just I wanted to make that clear. So, for example, here is um, 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 so this is descriptive statistics and describing the data through frequencies. So here on the rows, I have basically I have the frequencies listed for who experienced a CHD event or not. So the no is no CHD event, yes is yes, of course, they had CHD event. What is the total number of participants in the study? 3,154. Of this, 2,897 said no, they did not experience a CHD event, and 257 said yes, they experienced a CHD event. So, what is that percent of the total population? That is 257 over 3,154. Okay, so that's this 8.1%. So the 8.1% of the study participants experienced a CHD event. Very simple, frequency and proportions. Okay. Now another description of the same data. What are the odds? How many people are familiar with odds? Okay, so let's talk about, take time to understand odds. So in discussing binary variables, we can talk about odds in addition to probability. In the previous slide, we talked about percent or probability, right? 8.1% has CHD, experienced a CHD event. What is odds? So let P be the probability of yes. That yes could be CHD event, that yes could be cancer, that yes could be any binary outcome, like any binary outcome. Because there are only two possibilities, yes or no, what is the probability of no? That's just 1 minus P, right? Because the probability of yes plus the probability of no should add up to 1. So the probability of no is 1 minus P. Odds are defined as the probability of yes divided by the probability of no. So odds is P over 1 minus P. Okay. So in the example with CHD event, what would be the odds? It would be yes, probability of yes divided by probability of no. The probability of yes is 8.1 and the probability of no is 91.9, right? So it would be 8.1 divided by 91.9. Okay. What about if I asked you what are the odds of getting tails upon tossing a fair coin? Odds. The probability of getting a tail is half. What is the odds? Yeah, so it's 1, right? Because it's P over 1 minus P, half over half. Okay, what about the probability of getting a 6 when I toss a fair die? 1 by 6. The probability of, sorry, not the probability, the odds of getting a 6 when I toss a fair die. The probability is 1 over 6. What is the odds?
1/5.
1 by 5. Everybody,
Yes, minus
1 over 6 divided by 5 over 6, right? So it's 1/5. That's the odds of getting a 6 when I toss a fair die. What is the relationship between odds and probability? So here is a pictorial description of, oh, that mark is still there. I feel so sad. So responsible.
You can sponsor for the whole.
Yes, I can.
We desperately need the book of it.
Yes, of course.
I'm sure you have heard multiple times that we are very close.
We actually had some discussion about that this morning. How we can leverage institutional support. So we talk about that. So here is the two depictions of the relationship between odds and probability. And as you can see, as the probability increases, the odds also increase. And in fact, the odds increase almost exponentially as the probability increases. Now, suppose, again, we can relax this, but I want to, in the introduction of categorical data, I want to keep things very simple. Suppose you also have a predictor that is binary, gender, it's going to make it up, smokers versus non-smokers, alcohol users versus non-users. Again, it's difficult to sort of categorize that way, but let's say so a predictor that is also binary. What we are going to talk about is what are some measures of association between the predictor and the outcome. In linear regressions, like for a single predictor and an outcome, you will usually do a Pearson correlation coefficient, then you will fit a linear model, slopes, and right. So here, let's see what are some measures of association between the predictor and the outcome. Again, it doesn't have to be a binary predictor. We'll start from there, but then we can relax it. So the first is, it could be the difference in probabilities or proportions. So if the difference in the probability of the outcome across the categories of predictor is something other than 0, then we would say that there is an association between the outcome and the predictor. For example, let's say gender, and we had CHD there. So we can calculate the probability of experiencing a CHD event for males, and we can calculate the probability of experiencing a CHD event for females. Each of those is a probability. We can take the difference of those two. Let's say it's 0. Again, we'll do hypothesis test and everything. If it's 0, then what are we saying? That there is no association between gender and experiencing a CHD event. So that's one way of understanding the association. What about, let's talk about another quantity. So now let's translate the odds. So the ratio of the odds, that is what is called odds ratio, is also a measure of association. So what is odds ratio? Odds ratio is the odds, in this case, odds of experiencing a CHD event for males divided by the odds of experiencing a CHD event for females. So it's the ratio of two odds. Yes, that is what is called the odds ratio. So it's the odds of one category of the predictor divided by the odds of the another category of the predictor. And if the odds ratio, which is usually abbreviated as OR, is different from 1, then we say that there is an association between the predictor and the outcome.
Can you use some number to like ratio of one divided by the other? And if it's different from one exactly.
Yeah, we'll talk about it at length, but let me just tell you. Yeah, this is just gently in kind of getting into that. Uh, yeah, but she's asking like, give an example of a number. Let's say, and like I said, talk about it at length. But let's say the ratio of the odds for experiencing a CHD event for males versus females is, I'm just making it up, 2.1. It's different from 1. You will do statistically, kind of significance test for the 2.1. Is it different from 1? But that comes later. So what does the 2.1 mean? That 2.1 means that males have a 2.1 times higher odds of experiencing a CHD event compared to females. That's what the odds ratio is. And it's very easy to interpret when the predictor is also binary or categorical. Again, as I said, we can relax it and we will relax it later. What if the predictor is continuous? Let's say continuous age. So what does odds ratio mean? So in that case, let's say the odds ratio for age, which is continuous, is I'm going to sort of make up. So it's say 1.2. And let's say age was analyzed as a continuous variable, but in 5-year increments. Yes, so 1.2 odds ratio means for every 5-year increase in age, the odds of experiencing CHD event goes up by 20%. So what are we doing there? We are taking the 1.2 minus 1, which is the hypothesized value, divide by 100. Sorry, multiply by 100. Okay, so that's the interpretation. So depending on whether the predictor is continuous or categorical, the fundamental concept is still the same, but you kind of do the trick a little different. Okay, so now hypertension and CHD events. Let's say I bring in a predictor like hypertension. So I will define hypertensive if systolic blood pressure is greater than 140 or diastolic blood pressure is greater than 90. So that's my definition of hypertensive. So now I'm saying among those who are hypertensive, what proportion had a CHD? So that's a probability. And then among those who are not hypertensive, what proportion had a CHD? And is the difference of probability something other than 0? That's one way I can answer the question if there's an association between hypertension and CHD. The other way that equivalently I can answer this question is that among those who are hypertensive, what are the odds of CHD? And then what are the odds of CHD among those who are not hypertensive? Is the odds ratio different from 1? Okay, so that's the basically idea. So now in analysis of categorical data, the sort of the univariate analysis. Univariate means that you're trying to understand the association of outcome with a single variable. Okay. So this is sort of parallel of simple linear regression, analog of simple linear regression in the categorical data setting. So what we do traditionally or typically, we construct a 2x2 table. This is called a contingency table. Why 2x2 here? Because outcome has 2 categories, yes, no. Now my predictor also has 2 categories, hypertensive, non-hypertensive. My predictor could have more than 2 categories. So there I would construct a 2 by k table. Depending on what k is, k could be the number of k is the number of levels of the predictor. Say for example, if the predictor is race ethnicity and I have 5 categories of race ethnicity, then I'll get a 2 cross 5 table. Okay, so here I have a 2 by 2 table. And do you see how the 2 by 2 table is constructed? So on the rows, I have the outcome. CHD event, no, yes. And in the columns, I have the predictor, hypertensive or not hypertensive. And now, based on this 2 by 2 table, I can calculate the probabilities and or the odds in the previous slide. So let's do that. So here is the, again, the same 2 by 2 table. So now, let's say I want to calculate the probability of CHD. First, I already showed the slide, but let's say among patients who are not hypertensive, what is the probability of experiencing a CHD event? It will be 173 over 2485. So that's a 6.9%. Yes. What about among patients who are hypertensive? What is the probability of experiencing a CHD event? It's 84 over 669. So it's 12.6%. Okay. What is the difference between this? Because remember, that's what we are after. So the difference between this is about 5.6%. So this is in terms of the probabilities. What about in terms of the odds? So now let us calculate the odds of CHD among the hypertensives and non-hypertensives. So among the non-hypertensives, what is the odds of experiencing CHD? So it's P over 1 minus P. So 0.0696 divided by 1 minus 0.0696. Yes? Just P over 1 minus P. So it's about 7.5%. What is the odds of CHD among hypertensive patients? So again, it's P over 1 minus P. So 0.126 divided by 1 minus 0.126. So that gives me a 14.4%. Okay. What do we do with the odds? Do we take the difference?
What's ratio?
We take the ratio, right? So what is the odds ratio? So we take 0.144 divided by 0.748. Oh, did I do this calculation wrong? Ooh. না, into 100 হবে, কিন্তু did I do a... Oh, no, okay, so it's just a typo. I have just a typo. No, because I wrote it as 0.748. So this is, so please correct this. This is 0.0748. So basically, I take the ratio of those two and I get a 1.91. This is my odds ratio. So who wants to repeat what the interpretation of this 1.9 is? We just talked about it. Say it again. No, I'm not talking about significance now. I don't know.
The hypertensive has 1.9% more chance of having CH compared to the normal.
1.9 times.
Almost double the chance.
Exactly. Hypertensives have 1.9 times higher odds, not chance. Chance and odds are not the same. Chance is the probability. Yeah, this is a very, very fundamental thing. So can we again talk about it? Because my hope is after we kind of get out of this workshop, you will be reading like a paper in a clinical journal more accurately than someone else outside this classroom. Okay, so that's why it's important to understand that chance and odds are not the same. Chance is the probability, that P. Chance is also sometimes referred to as risk. Risk is probability, but odds is not probability. Odds is the ratio of the probability over 1 minus itself. Okay, so here the interpretation is that hypertensives have a 1.9 times higher odds of experiencing CHD than non-hypertensives. Make sense?
I have a question.
Sure.
Like, for the ratio 1.9 here. So suppose if we had made a probability ratio,
Probability ratio.
then also we have got 1.9 around it. Like 0.126 divided by 0.069. So but why create the inequalities when we can have a probability?
Um,
But technically what it will happen is 1.9 times odds means what? Yeah.
That's a very fundamental question. So let's try to see if I can, without showing any map, whether I can explain that. So what you talked about is the ratio of the two probabilities. There is a name for that. In fact, it's called risk ratio. Right? Risk ratio is another quantity. Okay. So first things first. Why did we have to, instead of doing a risk ratio, why did we have to translate into odds and then do the, do it as ratio of odds? And that reason is purely mathematical because remember, we are going to take this into a regression framework. That's what logistic regression is all about. It's much analytically much difficult to model the ratio of the risks than the ratio of the odds, because the ratio of the odds, you will see beautifully, it sort of lends itself to an interpretation in the logistic regression model where you take the coefficients, you exponentiate, and you get back your odds ratio. And that has to do with the underlying shape of the distribution of what we are modeling. So it's a purely analytical, like a mathematical explanation. The other thing that I'm going to say is still often investigators are prone to say, I don't understand odds ratio. I would rather understand risk ratio. Because risk ratio, as you just said, risk ratio is much more interpretable to me. Like when you were saying that, hypertensives have a 1.9 times higher chance of CHD than non-hypertensives. So that's where, again, this is statistics at the fundamental level is again it's a lot of math, but it's really beautiful math. But I think it's even more what is beautiful is these interpretations and how they are intertwined. So here is the story about risk ratio versus odds ratio.
So one thing in this scenario you always be thinking about is that, like for example, I'm doing some intervention, suppose a drug for a disease, and like the chance of getting cure for the disease, the drug A was 0.8%, and the chance of cure with drug B becomes 0.4%. Like if we make a ratio of these two risks, like if we make a ratio of these two probabilities, so the ratio would be 2.
Yeah.
Double. But if I get that
is RR is
2, but if I get the absolute risk difference, that is only 0.4%. That's not clinically significant.
Yeah.
So like when I see this ratio, it seems as if it is hugely effective. But when I don't see the ratio, when I see the absolute difference, I see that it's not that effective.
Yeah. No, and that is a different question. That is like clinical significance versus statistical significance. And only you can tell us like what is clinically significant. But that's a different question. But let me come back to your question and your question about risk ratio versus odds ratio. So as I said, the reason why we do it in terms of odds ratio is analytical, is mathematical. But there are situations where the odds ratio is kind of, or the risk ratio is kind of approximately equal to the odds ratio. So people can take this 1.9 and make a statement like you did. Roughly, hypertensives have twice more chance of CHD than non-hypertensive. What are those scenarios? That is connected with the study design. So most of you probably do cohort studies. In case control studies, that equivalence between risk ratio and again, I like I have some slides about study design to talk about yesterday, but again, we ran out of time. When you have a case control design, this equivalence does not hold. But when you have a cohort design, you actually can say approximately the risk ratio is equal to the odds ratio. And again, mathematically you can prove that, but this is something to keep at the back of your mind. If you want to be totally correct, and if you don't sort of know about the underlying study design, then as you will see, most journals in their like the papers would report odds ratios and the 95% confidence interval. But there are some that would say RR, meaning risk ratio. And that's where it comes from. Like if you have a cohort design, so you are following people over time, then you can actually approximate the risk ratio by the odds ratio. So that's the sort of the take home. And also, if it's a sort of a rare design, again, rare disease, again, there are sort of parallels, equivalent. So, what does it mean by rare disease? That the probability of having the disease is very small. So 0.05 divided by 0.95, let's say, and 0.02 divided by 0.98 is almost equal to 0.02 divided by 0.25. Why? Because the 0.98 and the 0.95 denominators are like almost 1, right? So you are dividing or by quantities almost equal to 1. Actually, somebody pull out your calculator and just tell me. So 0.22, so it's a rare disease, let's say. I know we are digressing, but that's good. 0.2, it's a rare disease. The chance of having the disease is 0.22 over 0.05 for two categories of the same predictor for, let's say, gender. Okay, so whereas, so that's the ratio of the risk. Now, if you do the ratio of the odds, it's 0.22 divided by 0.98, right, on the top. And then on the bottom, you have 0.05 divided by 0.95. What do you get in these two scenarios? Huh?
0.9.
Yeah, because odds is 0.02 divided by 0.98 ওপরে আর নিচে হচ্ছে 0.05 divided by 0.95. আমাকে অঙ্কটা করতেও হবে না, আমি বলে দিচ্ছি যে ওটা 0.4 এর খুব কাছে একটা।
ফার্স্ট একটা 0.4
হ্যাঁ, পরেরটা কি এলো?
Actually, I have what right. Like you said, if it is of the content is significant, that's all right. What? Which one is like যেটা বলতে
আমি সিগনিফিকেন্সিটা এখনো জানিনি।
okay.
কারণ সেটাও একটা স্ট্যাটিস্টিক্যাল টেস্ট অফ হাইপোথেসিস। সেখানেও ভেরিয়েবল অদৃশ্যও একটা ভেরিয়েবল আছে, স্যাম্পলিং ভেরিয়েবল।
হ্যাঁ এখনো আমি যাইনি সিগনিফিকেন্ট আমি আপনাকে সিগনিফিকেন্ট করছি so the question was risk ratio versus odds ratio so again let's say CH outcome টা হ্যাঁ yes no আর predictor টা হচ্ছে কি বললাম আর এটা হচ্ছে yes ঠিক আছে আচ্ছা রিস্ক রেশিও কি হবে রিস্ক রেশিও হবে রিস্ক রেশিও হবে probability of yes for males let's say divided by probability of yes ঠিক আছে আমি বলছি যে রেয়ার ডিজিজ হয় হ্যাঁ মানে probability of having CHD is very small রেয়ার মানে আরো রেয়ার পয়েন্ট males এর 0.01 আর females এর 0.005 okay what is odds ratio odds ratio will be PM divided by 1 minus PM so this is the odds of CH males and females is PS divided by 1 minus PM so this is equal to going to be 0.01 divided by 1 minus 0.99 right আর তলায় হচ্ছে 0.005 আরো ছোট divided by 1 minus 0.995 তাই তো এবার আমি বলছি এইটা ক্যালকুলেটরে লিখে বার করতে I know we are digressing but these are all good questions
এটা পুরো কম্পিটিশন সম্ভব কারণ রিস্ক রেশিও আমরা করি হচ্ছে যখন মানে দুটো রেশিওতে বার করছি তো আলাদা আলাদা মডেলের ক্ষেত্রে একটা
না।
ওভার স্টাডির জন্য আর একটা হচ্ছে কেস কন্ট্রোলের
না 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 এটা সেম স্টাডিতে করছি আমি বলছি যে রিস্ক অফ হ্যাভিং একটাই কোভেরিয়েন্ট আছে এইটা এইখানে আমি বলছি যে forget about the study design all that I'm saying is the disease is very rare মানে the chance of এটা ঠিক নয় context the example টা কারণ chance of CHD is much higher than 1% but treated as if we have a very rare disease
odds ratio তো বার করতে তোমাদের কেস কন্ট্রোলের ক্ষেত্রে odds ratio বার আর ওভার স্টাডি কিন্তু সেখানে আমরা রিস্ক রেশিও বার করি
না প্রশ্নটা ছিল odds ratio আর risk ratio এর মধ্যে সম্পর্কটা কি what is the relationship I'm saying in general they are not the same there are study designs where you can show that the odds ratio and risk ratio are approximately the same as in cohort studies risk control এর ক্ষেত্রে odds ratio বার করা যায় odds ratio বার করা যায় হ্যাঁ কিন্তু এটা আমি বলছি এটা আমি আরেকটা অন্য জিনিস বলছি আমি বলছি if the disease is rare forget about then also you can show that these are the same এখানে কি বেরোলো এটা তো 2.0 কোথায় কোথায় কোন odds ratio এটা odds ratio হ্যাঁ আর what is আর তো দেখে যাচ্ছে হ্যাঁ আর এটা কি বেরোলো 2 that's the thing তো আমি এটা কি বলা যায় গন্ডগোল
They are artificial. They are
so this ratio to be as r is equal to r তাই তো এটা ইন জেনারেল ট্রু আমি জাস্ট একটা মানে সংখ্যা পেরে দেখালাম but in general true so the question that Dr. Kaushik had to step out that Dr. Kaushik was asking again
there were several parts to the question. One is that, and you also asked that, আমি তো risk ratio বোঝাটা আমার পক্ষে অনেক সহজ। However, এই odds ratio আবার, the reason why we do that is analytical, কারণ মডেল করতে সুবিধা হয়, হ্যাঁ? Rather than modeling like the ratio of two probabilities, modeling the ratio of odds from an analytical point of view is easy. But you might still say, আমি still চাই risk ratio দিয়ে interpret করতে। This difference we all agree যে doesn't serve our purpose. So then my point is two points. One is odds ratio you can calculate for any design. But risk ratio you cannot calculate for every design. You can only calculate for cohort design, cohort studies. Into there's another situation where the risk ratio and odds ratio can be approximately said they are the same. That's for rare. Rare disease মানে হচ্ছে the probability of the ordinary disease is very very small. So এখানে আবার আরো অনেক কিছু মানে I can sort of go on and on because all of these things are connected. Rare disease বললেই তখন আমরা ভাবি যে তখন না standard logistic regression doesn't work. তখন আমাদের অন্য ধরনের মডেলিং করতে হয়। I don't know how many of you have heard about like negative binomial, that kind. But this all is tied to the regression framework. All of it is so you have to be very careful about interpretation. আমি যদি কিচ্ছু না জানি about the design, which brings back to your point, then I would speak just like I corrected her that no, it's not chance, it's odds. I will make the statement in terms of the odds. Process মানে হ্যাঁ superior মানে সেটা তো আবার formal test of hypothesis করতে হবে কিন্তু so now your predictor becomes intervention দেওয়া হয়েছে কি হয়নি, it's again like a binary predictor. Yes, exactly. Cohort studies এর ক্ষেত্রে you can say যে odds ratio বার করা হলো logistic regression এ, কিন্তু you can interpret it as a risk ratio, chance হিসেবেও বলা যায়। That's the point. Did I answer your question? কি নাম? Obhinav, did I answer your question? So bottom line is odds ratio you can interpret across all study designs and you can obtain across all study designs. But only for cohort studies does it have the risk ratio. And also for rare disease. Turns out that it's good.
I have a question.
Sure.
Just thinking out loud, correct me if I'm wrong. So as you said that odds ratio we can use across all kind of studies and case studies. But in case of cohort studies, we can use
You can interpret the odds ratio as this.
Okay. But you said that this equivalence probably goes to it's a rare disease.
Probably not. Yes.
It's almost equal.
Yeah. So the way we write it, actually, maybe that's how we should write it. So for rare disease, we can show again. We can show this mathematically that the ratio is approximately.
In case of the cohort studies, what we usually do is that the exposure has happened and follow them up and see whether they are developed the outcome.
Yeah.
So that usually holds true for outcomes which are not that rare. On the other hand, case control studies like to move from the outcome and then find out the exposure because the outcome is rare. So this becomes a bit like contradictory.
No, you have raised a very good point. So case control study, if I can, I'm again going to switch to Bengali a little bit. Case control studies, আমজনতা case control studies এর জন্য you should stick to the odds ratio interval. But for case control studies that are kind of at a rare disease, let's say then it's a rare disease, so I'm going to use the odds ratio to approximate the distribution. Does it make sense to conflict in A?
For example, just বলছি simultaneously just আমার point of view আমার কাছে কিছু বাচ্চা some children have developed have some risk factors, others don't. Yeah, now AKI is a rare incidence, but it's not that common. So then I want to follow up how many among this will develop the disease. AKI, but yes. But in that case, since AKI, supposing it's a rare phenomenon, because it's not that rare, but supposing it's a rare phenomenon, in that case, probably my if in that case, probably my risk ratio and my odds ratio, if it's not a rare disease, then the people not be good.
Yeah.
And then in that case, because I do cohort studies for outcomes which are not that rare.
Yeah.
So in that case, my cohort studies, am I right if I use risk ratio instead of odds ratio?
Like again, generally, I see where your confusion. So let's kind of go back and maybe just for your talk. Odds ratio is the quantity you can obtain and interpret for any study. And typically that's how you are sort of present your data, present your results. If that gives you ease of mind, stick to odds ratio. But some people sometimes like to interpret it as risk ratio. My point was risk ratio and odds ratio are not the same for all types of studies, for all types of. There are certain instances where these are going to be approximately the same. In your instance, we can approximately interpret the odds ratio as a risk ratio.
But here we have the genders as well, so we cannot predict. It is just RR is same as what? Rare disease has got that is same as odds ratio. But we have also the genders, male and female.
Yeah.
So we cannot talk about that. In general, it is same.
No, male and female could answer. Probability of the rare disease in male versus probability of the rare female.
So এই যে রেশিওটাই তো এটা কি মানে
জেন্ডার এর জন্য
ফিমেল এর বেশি না মেল এর বেশি
এটা মেল এর বেশি মেল এর বেশি হ্যাঁ
So there are other words I would like to ask. Is that also an external my own study? Because of which it is okay to use RR ratio.
in that part unfortunately I cannot sort of I have to show you the math and that's why I said it and even though you can আমরা odds ratio odds এর থেকে model because of the nature of the distribution. But remember, binary outcome to 1 or 0. Linear regression কি করি আমরা লিখি y equal to sum x হ্যাঁ একটা continuous outcome এখানে outcomeটা 1 or 0. So if you try to fit a linear summing up later, if you try to fit a linear model with a 1 and 0, তাহলে it fails because linear regression breaks down there. You have to model it as probability. And probability scale যখন মডেল করা হচ্ছে actually it's summing up. তখন না ওই p এর p হিসেবে মডেল করলে অসুবিধা আছে অ্যানালিটিক্যালি সেই জন্য p over 1 minus q odds এর থ্রু দিয়ে মডেল করা হয় logarithm of the odds সেটার এক্সপ্লেনেশনটা পুরো অ্যানালিটিক্যাল এবং ওই কেস কন্ট্রোলটা কোহর্ট সেজন্য আমি বলছি মেবি I said too much maybe I confused it that way so stick to odds ratio that's something that
yet for all studies.
সেটাই আমি বলতে চাইছিলাম তাহলে ফাইনাল হচ্ছে দ্যাট ওয়ার্ডটাই আমাদের দেওয়া বিকজ মোস্ট অফ দ্য
Exactly.
জার্নালে ওয়ার্ডই
Most journals will report OR. That's because again there is মানে OR টা যে কোনো স্টাডির জন্য ক্যালকুলেট করা যায়, যে কোনো স্টাডির জন্য ইন্টারপ্রেট করা যায়. That's why I corrected, I don't know what the name is. Yeah, that's why I corrected Dr. Kia that no, don't interpret it as chance. So it's the ratio of two odds. So maybe I confused you more by giving you all these details.
I have a question.
Sure.
Maybe we digress a bit. When I see the ORs and actually when the doctors want to counsel the patients, so how do they explain that? How do they explain the odds ratio? And when you encounter a hypertensive, then you really say that this is your odds of getting a CHD event. How do
Yeah,
they
I know. That's exactly why, you know, basically we had all this discussion. মানে যে আমি কি রাফলি মানে বলতে পারি? That's what happens. Roughly people বলে, but when you can like tell the and especially for rare disease you can definitely for cohort studies you can definitely, but you as the sort of the clinician scientist, you should understand the disease. When you are kind of explaining to a patient, even risk ki বোঝানো যায় না, right? Risk of disease, risk is the probability বোঝানোটা মানে for lay audience very tough. সেখানে odds বোঝানোটা তো আরো tough.
when we would be technically correct, who's that extent for patient that
Yeah, and that's what happens. That's what happens. That's what you do. But like I said, as a clinician scientist, you have to understand. And again, as Dr. Sinha was saying, what do I report in the journal? The journal you report obsession. This is all very good discussion, but you know, make sense? Okay. So there is a shortcut এবং এইগুলো এই ধরনের প্রশ্নগুলোই আসা উচিত কারণ this is what you know kind of needs to be clear. So odds, yes, odds বোঝানোটা একজন lay person কে is very difficult.
clinically or significance relative risk की हमें better causes.
Exactly. Yeah. So relative risk দিয়ে বোঝানোটা relative risk is basically a risk ratio. Okay. Acha, there is another way to calculate shortcut to calculate odds and odds ratio. একটা odds টা হচ্ছে ওই যে বললাম yes in hypertensive non-hypertensive group is 173/2312 or in hypertensive group it's 84/58 oh where is the 585 coming from? Oh sorry, yeah, 173/2312 and 84/585, right? Yeah, and then you can calculate the odds ratio also in a shortcut way where you take the cross product of 2312 with 84 and divide it by 585 times 173. Again, it's just simple arithmetic in a 2x2 table. 1.91 again. আচ্ছা এইবার হচ্ছে যে প্রশ্নে the p value. I'm trying to shift you away from p value, but you just have to leave this value. Okay, so your significance এবং আমি এতক্ষণ বলেছি যে no, I haven't talked about significance yet, so this is where it comes. First we are going to do it. I don't know whose question it was it Abhinav, your question যে আমরা দুটো proportion কে কেন ডিফারেন্সটা risk ডিফারেন্সটা কেন দেখছি না? So first let's do it with risk difference. So risk difference মানেটা কি? We take those two probabilities and it's a difference in the probabilities, right? So first we are going to do a 2-sample test where we are comparing the probability of CHD in the hypertensive group
versus the probability of CHD in the non-hypertensive. So if there is no association between hypertension and CHD, তাহলে আমি কি expect করবো যে এই probability দুটো same. So I write the null hypothesis as the P under for the hypertensive group minus the P for the non-hypertensive group is 0. Or the alternative হচ্ছে the P of the hypertensive group minus the P of the non-hypertensive group is not equal to 0. Yes, it's exactly what Abhinava asked. Can this difference, Abhinava, sorry, Kaushik asked, like what is the, sorry, I'm calling everyone by their first name, if that's okay. America said, সেটাই চলে. So, and you can call me Mo. So, Kaushik যেটা বললো যে আমি একটা 8% একটা 4%, আমি দুটো ডিফারেন্স মিলে এইরকম দাঁড়ায় আর odds ratio মিলে এরকম দাঁড়ায়. তো ডিফারেন্সটা নিয়ে আমি কেন টেস্ট করতে পারবো? So this is basically testing the two. Okay. So now what is the test statistic? This is what we call a two sample test. Two sample t-test যেমন আমরা করি continuous outcome এর ক্ষেত্রে. This is a two sample test for a binary outcome. আর binary outcome এর ক্ষেত্রে the quantity is proportion or probability or risk. So we are comparing two proportions. And this is the test statistic. Again, you don't have to remember the ugly formula expression. All you have to know is that this is the probability or for a binary outcome. Just for a continuous outcome, we assume a normal distribution on the famous bell-shaped curve. For a binary outcome, the distribution that we assume is what is called the Bernoulli or a binomial distribution. Binomial distribution. It's a discrete distribution, and I had a slide like that yesterday. So coin toss বা die roll করে মানে কটা হেড পাচ্ছি, that is a binomial distribution. Coin toss করে আমি 10 বার যদি টস করি, what is the chance of getting 4 heads? That is a binomial distribution. So this is a binomial distribution. Under the binomial distribution, again, I can construct a test statistic. I can compute again a p-value. And in this case, the p-value is ওই যেটা বলছিলেন আপনি 0.00004. 5টা জিরোর পরে 4. So if you are reporting this, you would basically report it as 0. Because the probability is so minusculely small, you are saying that it's extremely unlikely that you will get a result like this if indeed there were no difference between the hypertensive and non-hypertensive. So what would you do? You would reject the null hypothesis. So when you reject the null hypothesis, your conclusion is that the probability of CHD among hypertensives, this was, remember, the P was 12.6%. That differs significantly from that among non-hypertensives, which was 6.7%. Therefore, there is an association between hypertension and developing a CHD. Does that make sense? আমি আশা করছি এই স্লাইডটাতে এক ঢিলে বেশ 4টে পাখি মারা গেছে. একটা হচ্ছে পি ভ্যালুর পাখি, একটা হচ্ছে রিস্ক ডিফারেন্স, মানে ডিফারেন্স দিয়ে কিভাবে অ্যাসোসিয়েশন বলতে পারি সেই পাখি, আর একটা হচ্ছে রিপোর্টিং অফ পি ভ্যালু পাখি. Does that make sense?
In general, 3 decimal উপর করা দরকার. Should not say like this 5 not 4.
No. And most journals would kind of, if they accept you, the editor will come back and say, just report up to 3 places of decimals. Any questions on this? Kiran, you wouldn't believe sometimes how easy it is to explain statistics when you can speak in Bengali. I never teach statistics in Bengali, but maybe I do have a career here. Make sense? Okay. So now remember I said you can do it two ways. One is with the probabilities and difference in the probabilities. The other is through testing the odds ratio. So both will give me p-values. So let's do it with testing the odds ratio. So odds ratio ক্ষেত্রে what would be the null hypothesis of no association? মানে there is a no difference in the odds between hypertensive and non-hypertensive. তাহলে the ratio of the odds কি হবে? 1. So the null hypothesis value is that the odds ratio is 1 and the alternative is it's not equal to 1. Okay, so let's do this. If odds ratio is larger than 1, then the odds of CHD among hypertensive are larger than among non-hypertensives. If the odds ratio is smaller than 1, then we are saying that the odds among hypertensives are smaller than the odds among non-hypertensives. That's the interpretation. এবার একটা জিনিস যেটা I will talk about a practical note. So now we are going to answer, in the example, we got the odds ratio to be 1.91. And you were trying to say significance. I said, wait, I haven't talked about significance yet. So now we are going to ask, is that 1.91 significantly different from
That's
1?
what I was asking. Yeah.
Right?
Yeah.
Yeah. So I did not go there yet when you asked that question. And that's why I said, no, I don't know yet because I have to test whether that 1.91 is statistically significantly different from 1. So why was I saying that? Because remember, the odds ratio is also like an estimate. The odds ratio also has a sampling variability. Again, think about the repeated sampling sort of philosophy that we talked about. I send each of you to draw a random sample from the same population and report your CHD and those variables, CHD and hypertension. Based on each of your sample, you calculate an odds ratio. You plot the histogram. So the odds ratio also have a sampling distribution. So that's why just because it's 1.91, I don't know the variation unless I do the repeated sampling approach. So I don't know if I gave you a 1.91 or if you told me it's 1.91, I cannot tell you right away whether it's significant or not. Most likely it is here. 1.9 is still kind of pretty big, right? But I cannot tell you, like what about 1.2? I cannot tell you if it's significant or not unless I do again the hypothesis test or confidence interval. Okay, so that's why I was saying, wait, I haven't talked. The other thing that I'm going to make as a practical note, এটা actually practical note is more যখন ওই interpretation এর ক্ষেত্রে. This is my experience and you might tell me no, you're wrong. My experience is that clinicians find it easier to interpret an odds ratio bigger than 1, but they kind of fumble if it's less than 1. Am I right? So I have worked with like many clinicians. That's what I do. Like so they have a much easier time interpreting the odds ratio of bigger than 1. They say, well, 1.9 times higher, 20% higher. So as a practical note, this is what I'm going to suggest you. Remember, only if I swapped the 0 and the 1, I would have gotten the odds of not experiencing CHD. So always when you are coding, এক্ষেত্রে আমি জানি hypertensive they are more likely to have CHD. সেজন্য always when you are coding the less favorable group, so your most favorable group you keep as the reference. মানে no hypertension is your 0 and hypertension is 1. কারণ তখন যেটা হচ্ছে you are interpreting like the odds for the hypertensives to experience the CHD compared to the non-hypertensives.
Normal person.
নর্মাল নন হাইপারটেনসিভ পারসন, হ্যাঁ। কিন্তু যদি উল্টো কোডিংটা করতাম, যদি আমি নন হাইপারটেনসিভদের 1 করতাম আর হাইপারটেনসিভদের 0 করতাম, তাহলে আই উড হ্যাভ গটন আ odds ratio less than 1. এবং তখন না ইন্টারপ্রিটেশনটা অনেক সময় আমি দেখেছি মোস্ট তারা একটুখানি চমকে যায়, ভাবাচাকা। So that's a practical no. Always code the less favorable category as a 1. মানে যেটাতে you would expect the outcome to be worse.
This at risk people.
At risk people. At risk people. Older people have a higher likelihood of experiencing. So older age you would code as 1 than younger age.
Biased হচ্ছে না।
Bias.
আমি করে ধরে তাহলে
আমি তো just for me to kind of for ease of interest. আমি তাদেরকে এক্সক্লুড করছি।
So or is very important.
Yeah, what is
What is our conclusion? Whether it is
we will come. Yeah. So I just stopped for those two practical notes. Okay, so how do we test this? This is the chi-square test. You all have heard about the chi-square test. একটা general comment, সেটা হচ্ছে chi-square testটা কিন্তু actually it's much more general than for testing odds ratio. So don't think that chi-square test, the only use of chi-square test is testing for odds ratio. It has much general use, but in the context of binary data, you can test the association through odds ratio using a chi-square test. Again, there is a little bit of math here. What it does is compares the observed count in each of the 2x2 cell with the expected count under the binomial distribution. And then you look at the conceptually, what is the difference between the observed and expected, and square it, take the sum. So just I wanted to have this slide on, not to show you the math, but to kind of conceptually tell you what is happening behind the scenes. And behind the scenes, what is happening, I don't know if you wanted to take a photo of the slide. What is happening is you are saying you have that 2x2 table of CHD and hypertension, where you had the frequencies, but you also assume the binomial distribution, right? So under the binomial distribution, if there is no association between hypertension and CHD, what would those counts be like in each of those 4 cells? You calculate that. Then you take the difference of the observed from the expected, and you compute the chi-square test statistic. You square those, you add them up, that gives you the test statistic. So this is analogous to in the regression context, the residual we were talking about, like observed minus predicted. We probably did not go into that yesterday, but that's why again the linear regression concept sort of carry over to this situation also. Okay, so here এখানে কি হচ্ছে? So this is the 2x2 table, and you can see now I have multiple rows for each cell. So CHD, yes, and non-hypertensive. I know that there were 173 people like that. hypertensive and experiencing CHD, there were 84 people like that. So these top values 2312, 585, 173, 84 are the observed counts. Below it, we have an expected count, and this expected count comes from the underlying binomial distribution we assume, and we say under the binomial distribution, if there is no association between CHD and hypertension, what would those counts look like? What would we have expected? Okay, so it gives you the expected. Now you take the difference between the observed and expected in each cell, you square them up and divide it by the expected, that gives you the chi-square statistic. Okay, so the chi-square statistic to পেলাম, p-value কি করে পাবো? কারণ chi-square statistic টারও একটা underlying distribution আছে. Actually, it is a chi-square. You can look up chi-square tables, but again, you can also get it from SPSS. The bottom line is, in this case, the chi-square value that I computed, 22.04, once I calibrate with a chi-square distribution, I get a p-value of 0.000, like very close to 0. Abar ota Dr. Sinha, probably it's a 0.0001 or 0.0003, but it truncates to 3 places after this. So I report it as 0.
এটাও বলে যে p-value জিরো না
হ্যাঁ, 0 না দিতে ওটা ট্রাঙ্কেট করে দেয়, মানে দিস ইজ ফর অল প্র্যাকটিক্যাল।
0.0001.
হ্যাঁ, মানে I don't want you to be hung up on that, because it's like the way it is, it's like it's a very, very, very small chance. Again, it's a journal convention.
ম্যাক্সিমাম জেনারেলি ওটাকে
তাহলে জাস্ট লেস দেন করে দেব, কিন্তু it's more of a journal. মানে I wouldn't be so hung up on. And the bottom line is it's nearly 0. That's what I'm saying. Okay, so now so the p-value is nearly 0. What would I then conclude? That I would reject the null hypothesis, and I would conclude that there is evidence to believe that the association between hypertension and CHD is interpretation. Acha. Conclusion: there is a significant association between hypertension and the odds of developing a CHD event. The odds CHD are 1.91 times higher among hypertensives than non-hypertensives. And it also gives you the confidence interval. And the confidence interval goes from 1.45 to 2.52. Can you see that the confidence interval can catch also a number like 1.46, 1.48? So that's also plausible. So what this is saying is that that there is a statistically significant association between hypertension and CHD. এবার আমি একটা প্রশ্ন করছি, suppose I got that confidence interval be 0.96 to 1.98. So what would be my conclusion? That 0.96 confidence, 95% confidence interval, I got 0.96 to, let's say, 1.98 or let's say 2. What would be your conclusion about the association with hypertension and
0.96 is less than 1. It's possible.
yes, so 1 is within that confidence interval, right? So 1 is within the 95% confidence. So basically, 1 would be a plausible number. So then I would not reject the null. And I will conclude that there is no evidence to believe that there is a significant. And we had this discussion yesterday how the confidence interval and test of hypothesis are related. So in this context, that's what.
CI যদি 0.05 এরকম থাকে তাহলে
CI মানে confidence interval is always two numbers. It's an interval. It's an interval. It's not a single number.
রেঞ্জ হলে আমরা বলতে পারবো
ওইটাই যদি 1 থাকে ওই ইন্টারভেলের মধ্যে
হ্যাঁ
তাহলে ইটস নট সিগনিফিক্যান্ট আমি আমি বলেছিলাম 0.96 থেকে 2.1 1 ওর মধ্যে আছে how about let me give some other examples এখানে 1.45 থেকে 2.52 1 নেই ওই ইন্টারভেলে সুতরাং it's statistically significant. What about 0.88 to 1.2? Not statistically significant, কারণ 1 রয়েছে. How about 0.34 to 0.78? Significant. কেন? কারণ 1 নেই এবং সেখানে বেসিক্যালি আই এম সেইং উল্টোটা lower odds.
yes
Lower odds.
lower that's what you want
হ্যাঁ মানে the criterion is one cannot be in that interval. Okay, so relationships between the two tests. একটা টেস্ট হচ্ছে the z test to compare the difference in the proportions আর আরেকটা হচ্ছে the chi-square test to test whether the odds ratio is different from 1, right? Here is the good news. Both tests lead to same conclusion. Of course, they are equivalent. In fact, again, this is when math kicks in. The relationship between the two test statistics is if you take the square of the z statistic, you will get the chi-square statistic. So z square is equal to chi-square. Is this magic? No. There is solid math to show that this always will be that the square of z is equal to chi-square. And that's why these two tests are equivalent. So if you ask me, why don't I do like a test of the proportions? I will say, go ahead, do it, but you're going to get the same inference. In this case, the chi-square test for odds ratio and the z test for the difference in probabilities are exactly the same, and they will be. The advantage of the chi-square test is, আমি এখানে 2/2 টেবিলের জন্য দেখালাম. What if the predictor has more than 2 categories? Instead of hypertensive, non-hypertensive, let's say I have age group categories. 30 থেকে 40, 40 থেকে 50, 50 থেকে 60, 60 থেকে 70, 70 and above. It's 5টা age categories. Then it becomes a 2/5 table, right? So now I have how many probabilities? I have 5 probabilities if I want to do it that way. It's much easier with through chi-square test of the odds ratio because now I can do a 2/5 table. I can compute the odds ratio, and I can do a chi-square test. So it's very easy to do it that way, and the z test really cannot compare. Why are we messing with odds ratios? If the tests are the same, why can't we just focus on differences? Exactly the question Kaushik was asking. I'm sorry that he's not here now. In the probabilities in one group versus another, that's because, as I said, modeling differences in proportions while accounting for other factors, confounders, multiple predictors is a difficult problem analytically. কারণ আমরা তো এরকম সিম্পল ডোমেনে মানে থাকবো না যে একটাই প্রেডিক্টর চলো we will bring in lots of other variables, confounding factors, etc. And in that situation, analytically, it's difficult to work with the difference in proportions. Also, we cannot do linear regression on probabilities, what I was telling just like a few minutes back, because probabilities are bounded between 0 and 1. Whereas linear regression, আমি কি assume করি, y আমার outcome is normally distributed, a continuous variable. It can actually theoretically span the whole real line. It can go from negative infinity to positive infinity. Theoretically, most of the times we only use height, weight, LDL, we use a range, the positive axis. Into we cannot do a linear regression on the probability, because probability is only span between 0 and 1. So instead, what we do is we use the concept of OR to expand the analysis of tables into logistic regression. What if the predictor has more than 2 categories, just as I was saying, like age group? So we construct a 2 by k table. K is the number of categories in the predictor. We can describe the odds ratios between the reference category of the predictor and other categories. What about reference category? Let's say আমি বললাম যে age group 30 to 40, the youngest age group is my reference category. বাকি সবাইকে আমি compare করব against that 30 to 40 age group. That becomes my reference category. So I can calculate the odds ratios for each comparison, and then I can compute. Actually, let's go to the weight. So instead of age group, I had weight category. So I have weight in pounds. So less than 140, 140 to 170, 170 to 200, and above 200. এইগুলো হচ্ছে আমার weight. So I want to still understand the association between my weight and CHD, but now weight has more than 2 levels, just 4 levels. তো এবার আমি কি করব, তাহলে আমি ওই less than 140 যার most favorable হওয়ার কথা তাকে আমি রেফারেন্স বানিয়ে নেব, কারণ I expect from the nature of what I know about CHD that obesity is associated with CHD, right? So I expect that the 140 to 170, the 170 to 200, the above 200, they will have higher odds of having CHD compared to the less than 140 weight group. Yes, everybody with me? So ওই যে বলছিলাম না, একটা practical note, do you always want to, কারণ it's easier for clinicians to interpret a odds ratio bigger than 1. So that's why I make the most favorable weight category as my reference. কারণ বাকি সবার odds ratio গুলো একের বেশি হবে, সেটাই লাইক may not be statistically significant, but একের বেশি. Okay, so basically that's what I do. It's a 2 by k table. And now I calculate the odds ratio of each weight category using the less than 140 as my reference group. Everybody see what I am doing? It's almost like আমি এই টেবিলটাকে না, এই 2 by 4 টেবিলটাকে আমি না ভেঙে নিচ্ছি 3টে 2 by 2 টেবিলে। একটা হচ্ছে less than 140 with versus 140 to 170, আরেকটা হচ্ছে less than 140 versus 170 to 200, আরেকটা হচ্ছে less than 140 versus greater than 200. So I have broken it up into 3 2 by 2 tables, and once I have broken it up into 3 2 by 2 tables, I know how to calculate the odds ratio. We all saw. So these are the odds ratios. Okay, and what did I say? You would generally think that the অন্য গ্রুপটার odds ratio টা higher হবে than 1. It turns out the 140 to 170 age group compared to the less than 140 age group, sorry, weight group is 0.98, মানে ওই 1 এর খুব কাছে, মানে তার মানে এদের মধ্যে কোনো তফাৎ নেই। কিন্তু for the 170 to 200 and the above 200 group, their odds ratios are 1.68 and 1.66. So it's a no-brainer. আমাকে অঙ্ক করতে হবে না, আমি এই odds ratio গুলো দেখে বলে দিতে পারবো যে I think I will formally still do it. There is no difference between the 140 to 170 group versus the less than 140 group, but the 100 group has higher odds of having CHD compared to the less than 140, and similarly for the above. Right? So now I do this. I ask this question: is there a statistically significant association between weight and CHD? So I'll use the chi-square test. And when I do the chi-square test, I get a value of same way observed minus expected করে করে আমি chi-square টা বার করলাম, and 16.778, and the p-value is 0.001. So what would I report here? In journals, I would report 0.001. But interpretationally, again, the same thing. There is only a 1/1000 chance that I will get a result like this under if the null hypothesis was true. So basically, it's very unlikely. Tar mane, what am I saying? That I would reject the null hypothesis and conclude that there is a statistically significant association between weight and CHD, and the odds of having a CHD among those 140 to 170 are 0.98 times the odds among those who weigh less than 140 pounds. The odds of having a CHD among those 170 to 200 are 1.68 times larger than those with less than 140 pounds. And the odds of having a CHD event among those greater than 200 pounds are 1.66 times larger than among those less than 100 pounds. Yes, that's the difference. So again, the terms that we learned: odds ratio, 2/2 table, 2/k table, chi-square statistic. Statistics are কিন্তু মজার, সবাই ঘুরে করে রাখছে।
So is there anything that tells me that my confidence interval is too wide? Anything that tells me as much as acceptable? For example, like certain studies in our analysis we have found that the OR ranges 3.1. So that is a line. So when should I say that the confidence interval is probably acceptable?
No, there's nothing about it. There's nothing about what is acceptable or not, and there is not a single rule of thumb. For some studies, like if the confidence interval, like maybe in your study, the 14.1 limit is ludicrous, but there may be some studies where it is a possibility. When do you get?
So a study কোন স্টাডিতে এটা আসে যে the AKM কথা
হ্যাঁ, আমি আসছিলাম ওটাতে।
AKM or ratio in my study came as 2.1, and the confidence interval came say 1.4 to 14.1. তার মানে কিন্তু এটা তো আসছে যে this is significant.
Exactly.
This is আমার sample size টা যদি
that's exactly what I was coming to. So all কালকে যেটা বলছিলাম, if the error margin is wider, the precision is lower, the variability is larger. এবার variability larger, precision lower, error margin বড়, সেটা generally sample size এর জন্য হয়, কিন্তু sample size is not the culprit always. মানে blame it on the sample size করে that you should be again as a clinician scientist. That's why I said 14.1 may be a likely range, one end of the range in some studies. There are কখন আমি অ্যালার্ম হবো যে something is definitely wrong, আমি পেলাম 1.98 to 999 point something, তখন আমি কি জানি যে there is some weird distribution, it's an artifact of the distribution. সেখানে কিন্তু স্যাম্পল সাইজও না, an artifact of the distribution, some weird distribution. এবং খুব ইন্টারেস্টিংলি যেটা হয়, it's all about variations, that like without variation, right? So suppose you have a predictor, কিভাবে কি এক্সাম্পল AKI, এটুকু আমি জানি AKI ব্যাপার। Well, let me bring up another example. So let's say you have a predictor among the other, when you in your sample, the variable that you have measured, there is absolutely no variable. What do I mean by that? আমি just বলছি, এটা clinically may not make sense. Let's say I am saying that my predictor is blood glucose level if A1C greater than 8 versus less than 8. এবং আমি AKI এর সম্বন্ধে জানি না বেশি, কিন্তু pediatric population-এ unless it's a type 1 diabetes, I would expect that probably very few patients will have, maybe not, but hypothetically very few patients will have A1C, hemoglobin A1C greater than 8. তো এবার এরকম যদি একটা প্রেডিক্টর হয়, এখানে আমি যখন স্যাম্পলটা অ্যানালাইজ করছি, আমার আউটকাম AKI, আমার আরো অনেক কিছু আছে প্রেডিক্টর হিসেবে, কিন্তু আমার এইটাও আছে, hemoglobin A1C greater than 8 versus less than 8. এবার আমি দেখছি আমার স্যাম্পলে মানে 100 জনের মধ্যে মাত্র একজনের A1C greater than 8, বাকি 99 জনের A1C less than 8. ওই odds ratio-টা না, ওই কনফিডেন্স ইন্টারভ্যালটা would it trust me that there is no variable. You see how it is? So it's not, don't blame the sample size always. Yes, most of the times, but there could be weird sort of quirks in the data distribution. And ওখানে আমি দেখেই আমাকে আমার গ্রাজুয়েট স্টুডেন্ট রিসার্চ অ্যাসিস্ট্যান্ট ওটা নিয়ে এলো, এনে বললো যে I'm getting a confidence interval of like 1.98 to 999, and I'm like, it is statistically significant, but then I'm going to say, surely there's something. So let's do some detective work. Then I'll tell the person, can you pull up the distribution? And lo and behold, she will come back and say, there's only 1% with greater than 8 HbA1c. And that's when the confidence is, because why? Again, these are all connected. There's so much uncertainty in that estimate.
Sure. Suppose where my prediction
Multivariable.
So ma'am, in that case, is there that, for example, suppose the exact problem that we face, that we study analysis, there were some children with first nephritis, and we wanted to see what was the outcome in children, and we had various predictors like what was the age, how long after diagnosis started. So, and our overall sample size, there were only 3 kids of nephritis. So, the statistician madam, she said that since your sample size is so small, the logistic session probably not real time.
Yeah. So doing a multivariable logistic regression, I would sort of rephrase that. Um, it's again, it is nothing to do with logistic regression. It is about, and again, I mean, next time when we plan, we should kind of plan to talk about sort of the linear regression framework first. So there you are running into an issue of what we call small n, large p. What is n? N is the sample size. What is p? Number of predictors. So 30টা সাবজেক্ট আছে, সেখানে আমি একটা মডেল ফিট করার চেষ্টা করছি যেখানে 15টা প্রেডিক্টর, পার প্রেডিক্টর 2টো করে। লজিস্টিক কেন? যে কোনো রিগ্রেশন ফেল করবে। So I wouldn't make that blanket statement that doing a multivariable logistic regression is not a good idea. Doing a multivariable logistic regression with 15 predictors is not a good idea. But you can do it with predictors. 30টা লোক, and in that case, what I would do is I would say, let's say I'm just guessing about your study because I don't know what the study objective is. You have a primary exposure variable of interest, let's say, and you want to study the association between that variable and outcome. So you have done the sort of the univariate logistic regression, but now you say, I think age confounds that association. Bring in age. Gender confounds that association. Bring in gender. So there is kind of a tipping point beyond which it will fail. But you can fit a logistic regression on a sample size of 30 with like 2-3 variables. But you have to scientifically kind of approach it. You cannot just throw in things. You cannot say, ওইখানেই বলছিলাম garbage in, garbage out. কি হতে পারে, you may kind of run into the sort of the desire, okay, 15টা প্রেডিক্টর আছে, আমি স্টেট ওয়াইজে ফেলে দিয়ে দেখি না কি বার করে। বার করবে, garbage বার করবে। So you are the modeler, you are the scientist, you are the so as a model building philosophy, you always have to first, and this is where I think statistics is a science, because you involve biostatisticians right from kind of the design phase of your study. What is it that you are interested in primarily studying, and then build a model. It is not an automatic procedure. There has to be very careful science thinking underneath, and that's what happens. So, like I said, I wouldn't say it's not a good idea. Yes, it's a totally bad idea if you have 15 predictors, but you can sequentially, and you can say, okay, আমার primary exposure এটাতেই আমার আগে এটা দেখি, but এইটার association with the outcome, I want the most unbiased, honest estimates, and I know age confounds, I know gender confounds, so let me bring in age, gender. Okay, so it's 1:30. So shall I go on? We can go for another half an hour. Okay.
Study designing উপরে বলা হবে
আমার স্টাডি ডিজাইনিং উপরে
study design
হ্যাঁ, but study design আমি জানি না, we can, so this is what we plan. আচ্ছা কেউ কি
study design এগুলো কি একটা মাইনাস করে দিচ্ছি।
আচ্ছা একটা জিনিস একটুখানি বলি, তো some people are using, there is a QR code for evaluation of the workshop. Online please, কারণ we really like to collect data and get your feedback. কারণ তাহলে আমাদের পক্ষে সুবিধা হবে in the future to kind of,
Excellent. You
Thank
know,
you.
this, data collection for this as well. So,
Okay. Yeah.
evidence based.
Okay, please give your feedback.
Sure.
Thank
It was
you.
in the also, so registered, we have a good WhatsApp.
Yes,
Okay.
those who are not in, yes. But we would really appreciate you who are leaving, please do it today.
We know that.
Can I request you to
Scan the
that really? Acha. So this is how we structure, we can do it. So we are going to talk about logistic regression. And then the idea was like after we come back from the lunch break, it's an open session. You can ask me any questions. And should we do it that way?
There's a requirement for the study designs.
Study design I can go back and talk about. So I can talk about the different types of study design.
ওখানে অনেক সময় কনফিউশন হয় with the ethics code and other concepts.
ঠিক আছে, because we can talk about the study design. Yes. But we may not have time for to cover logistic regression in full if we sort of cut out on the time. But I'm happy to do either way. Okay. So what is the purpose of logistic regression? How is logistic regression different or similar to multiple linear regression or multivariable linear regression? And what is the interpretation of the parameters from logistic regression? So we want to model the probability of an event. How likely is a person to develop a disease? How likely is a person to quit their job after learning that they have an elevated blood lead level? Further, we also want to know what factors influence the probability of the event. Does developing a disease depend on the person's gender, age, etc.? Does the probability of quitting depend on how high the blood lead level is or the person's salary? Okay, so how likely is a person to develop CHD? আমরা এটা দেখেছি by looking at a 2x2 table that there was an association between hypertension and CHD and also between weight category and CHD from the 2x K table. However, hypertension and weight are associated, right? So এখানে কি বলছি আমি দুটো প্রেডিক্টরের মধ্যে association. So the question is, does weight confound the association between hypertension and CHD? This is confounding. And the answer is, yes, we can investigate that and we can adjust for this with logistic regression. So that's the framework, that's the multivariable framework. কারণ এর আগে আমরা কি করেছি, we took each at a time. We took weight category, we took hypertension. কিন্তু এবার আমি বলছি যে well, hypertension affects CHD, কিন্তু আমি এটাও জানি যে weight and hypertension have an association. বলছিলাম যে you have to first decide what is your primary exposure. So you come and tell me my primary exposure is hypertension. I want to understand whether there's an association between hypertension and CHD. So then I will tell you, okay, so then your primary focus should be how to get an honest, unbiased estimate of association between hypertension and CHD. You run a logistic regression model or a 2x2 table, you come back and tell me, okay, this is the 1.91 that you got. Then I will tell you, well, yes, but you haven't really adjusted for weight, you haven't really adjusted for age. Maybe it's not 1.91. After you have made, this is sort of the beauty and the nightmare of observational study. So are the people balanced in terms of their weight distribution, in terms of their age distribution? And the answer is of course no. This is observational study. So I'm going to say then, you don't know. I mean, it could also be because of weight. It could also be because of their age. So that's where this multiple or multivariable regression framework comes. Because now you want to adjust for weight, you want to adjust for age. Okay. So, I don't know whose question this was, but there was a question, why can't we model the probability? Why can't we model the risk? Maybe it was Obhinav's question or Kaushik's question. I don't remember. But, and I said, there is a analytical reason. So if we could model the probability using a linear regression, because remember, we are modeling the probability as an outcome variable, and the probabilities are always bounded between 0 and 1. So if we just completely forgot that probability is bounded between 0 and 1, and we said, oh, I'm going to fit a linear regression model to the probability, I would do miserably. I would fail miserably. The inference would be biased. It would also be nonsense results. Because the assumption for multiple linear regression is that the outcome is a continuous variable and the error is normally distributed. So, normal distribution does not have any bounds between negative and positive infinity. But probabilities can only be between 0 and 1. So linear regression will fail. So we need something else, and that something else is logistic regression. So the data from a given subject, we will have a binary response, yes, no. Actually, we could also have aggregate data, like in a 2x2 table denoting how many responded yes, how many responded. So the dependent variable y will be coded as a 1 or 0, representing yes or no. And we want to model the probability of yes, P. Probability y equal to 1. So I introduce a new sort of notation here, and this is what I talk about a lot in linear regression. But let me just tell you briefly. E within parenthesis y means, as statisticians, we call it expected value of y. Expected value of y means, on an average, what do you expect to happen?
This expectation value is also depending on the events. The number of events has evaluated on that particular
on that distribution.
How much time I have tossed the point, then I am calculating the expectation.
No, and that is if you have tossed it n times. Here I am saying that, let's say I have tossed it a single time. So the expected value of y is just p, because it's 1 times p plus 0 times 1 minus p. So it's p. But you are right. If I tossed n times, or if I looked at n subjects, then the expected value would be n times p. Right? So that comes from the distribution. So now, instead of modeling using linear regression, instead of saying my probability p is beta 0 plus beta 1x, remember again, expected value of y is p. Instead of saying that, we will use the log of p over 1 minus p. So the right hand side of the equation still says that beta 0 plus beta 1x. Into the left hand side of the equation now, linear regression ki hoy y equal to beta 0 plus beta 1x. Now I am replacing that y by log of p over 1 minus p. And this is what is called the log of odds. আচ্ছা, এইখানেই আমি বলেছিলাম যে কেন আমি এইটা করি instead of ওই p equal to beta naught plus beta 1x, সেইটার কারণটা হচ্ছে purely mathematical. কারণ analytically this becomes much more tractable for me. Okay, so that's why now my model is in a log odds scale. This is called a log odd scale. So the relationship, এবার একটু মানে ছোট্ট করে বোঝানোর চেষ্টা করি যে কেন P মডেল না করে log of odds মডেল করা হয়। I have on the y-axis odds in the left panel, and on the x-axis I have probability. In the right panel I have log odds in the y-axis and probability in the x-axis. Odds cannot be smaller than 0, right? Because it's P over 1 minus P. Our probability always goes between 0 and 1. Okay? কিন্তু log odds টা কিন্তু পজিটিভও হতে পারে নেগেটিভও হতে পারে, কারণ আমি ন্যাচারাল লগারিদম নিচ্ছি log base e। সুতরাং কি হচ্ছে, as the probability increases the log odds also increases. Anything that increases the probability will also make the log odds increase. সেই জন্য আমি ওটা log transformation নিই।
So basically, ma'am, what we're doing is we are converting the exponential term into a straight line by taking the log.
Yeah, almost. Yes, almost. এবং সেই কারণে, থ্যাংক ইউ ফর দ্যাট কোয়েশ্চেন, সেই কারণে এই যে লগ অডস এর থ্রু দিয়ে যে মডেল করছি না, এটাকে অলসো বলা হয় লগ লিনিয়ার মডেল। কেন? কারণ আমি যখন পি দিয়ে মডেল করছি প্রবাবিলিটি দিয়ে, তখন ওই মডেলটা ইট ফেলস বিকজ প্রবাবিলিটি ইজ বাউন্ডেড বিটুইন 0 and 1। এবার লগ অডস দিয়ে যখন মডেল করছি, অ্যাজ কৌশিক সেড, আমি এটা অলমোস্ট লিনিয়ার করে ফেলছি, রাইট? সুতরাং ওই যে লগ অডস যে স্কেলটা নেওয়া হচ্ছে, there is also a name for this in the sort of the statistical world. We say that the function that links the probability to a linear function of the predictor is log odds. So log odds is the link function. So ultimately আমি এটাকে মানে কৌশিক, again thank you for the question. Ultimately আমি এটাকে এমন একটা ফ্রেমওয়ার্কে নিয়ে আসার চেষ্টা করছি যাতে আমার অ্যানালিটিক্যালি কাজ করার সুবিধা হবে। And log odds does that, brings it to that same point. So that's why it's also called the log linear model. Does that make sense?
One question, why log base e, not log base 10?
Because again, log to the base 10, log to the base e, again it's calculus. Log 10 টা কাজ করবে না, কারণ এই লিনিয়ারিটি ব্যাপারটা কাজ করবে।
And because the graph of the left is exponential. So if we take the base e, then only we convert to a straight line.
কারণ নেচার অফ দ্য কার্ভ সেটা, the relationship between odds and probability, এটা এক্সপোনেনশিয়াল। এবার লগ 10 যদি নেওয়া হয়, ওটা কাজ করবে না, মানে ওটা ওই লিনিয়ার শিফটটা আসবে না। সেই জন্য আমরা
একরকম বস্তু আছে।
হ্যাঁ, সেই জন্যই তো বললাম অলমোস্ট লিনিয়ার। Again, this is not মানে এটা তো টেক্সটবুক এক্সাম্পল, রিয়েল ডেটা। Yeah, I mean this is in real data detection what. So this is also sometimes called the linear transformable to linearity model. কারণ আমাদের মানে কাজ করতে অনেক সুবিধে হয় যখন আমরা ওটাকে log linear model হিসেবে লিখতে পারি। এবার what is the transformation doing to the relationship between probability and x? আমি মডেল করছি log base c of p over 1 minus p। এবার সেটাকে আমি লিখছি that on equal to beta naught plus beta 1 x. X is my predictor. Now if I solve for p, what I will get is p P, the probability, because I want to bring it to the probability scale again, it will become exponential beta naught plus beta 1x divided by 1 plus exponential beta naught plus beta 1x. Once again, you know, this is the relation, this is a logistic curve. That's where it gets the name logistic regression. Probability as a function of the values of x looks like this. Probability is bounded between 0 and 1. So with this model, the predicted probability will be between 0 and 1, the way the probability should. On the other hand, আমি যদি একটা linear model fit করতাম to P, I could have obtained predicted values of P outside that 0, 1 range. I could have gotten a predicted probability of 2, which again is nonsense, or a predicted probability negative, which would be nonsense. But linear model, I can get predictions in the whole real line. Negative hote pare, positive. So that's what this transformation does to the relationship between probability and x. And what are the benefits of logistic regression versus 2x2 tables? The predicted variable does not have to be categorical. আমি দেখাচ্ছিলাম hypertension, weight, সব category করে দেখাচ্ছিলাম, কারণ আমি 2x2 table, 2x k table এইসব ফিট করে দেখাচ্ছিলাম। এখানে the predictor can be anything. It can be continuous, categorical, just like in multiple linear regression. That's the another fundamental thing. আমি যা খুশি measurement scale আনতে পারি on the right hand side of the equation. So yesterday, as I was saying, that what determines the modeling strategy is what is on your left hand side of the equation, right? So in linear regression, so y is continuous. Real. Then it's a linear regression. If y is binary, then it's logistic. Y is count data, like counting the number of malaria cases, certain county, a certain estimating cancer incidence. Then this is Poisson regression. If y is the additional complexity, y is like the time event data, time to death, time to cancer recurrence, time to organ failure. This is what I also call the sensory. Then the regression framework is what is called Cox's proportional hazard. Okay, so let's say this linear regression is the mother and father of all regression framework. However, there are of course some fundamental similarities, but there are lots of differences in these modeling frameworks. So much so that in a graduate program in biostatistics, each of them is one course, one semester long course. So I teach a semester long course on linear regression. I have taught a semester long course on logistic regression. Poisson regression will be a separate course. And this definitely will be separate.
So there are lots of like this builds the fundamentals and you go on, but there are lots of differences.
Poisson regression টা আরেকবার মানে কখন
Poisson regression হচ্ছে যে you are, let's say you are trying to model the incidence of a certain so it's a count variable. It's not a binary, yes, no, 0, 1. It's a count variable. এই কাউন্টটিতে 50 একটা ম্যালেরিয়ার আউটব্রেক হচ্ছে বা কোনো একটা এপিডেমিক আউটব্রেক হচ্ছে। এই কাউন্টটিতে 50 জনের হয়েছে। অন্য কাউন্টটিতে আমি জাস্ট 100 জনের হয়েছে। It's a count variable. So why? One thing comes from the fact that when you are talking about 50 জন versus 100 জন, it's not enough to talk about 50 or 50 জন, but maybe the number the county is only, I'm just making it up, 5,000. Whereas with the actual outbreak with the vanished, 3 counties. So there is a denominator also. You have to adjust it into account county size and all of that. So that lends itself distribution of, and moreover, by nature, the other thing can be continuous, it's a normal function and it can take values in the real line. I can have decimals, right? If I could measure, I would have weight as 142.76 pounds. Eta is a discrete random variable. I cannot have 6.82 people having malaria. So there is a difference in the nature or the measurement scale. If I have a categorical say deficient, sufficient, or yeah, how do I? Yeah, so that will fall in the general framework, but definitely an extension of, and that's why I said each of these 1 semester course. ওই একটা ক্যাটেগরিক্যাল আউটকাম দিতে পারে, সেখানেও আবার মজা আছে। এবার ক্যাটেগরিক্যাল আউটকামটা হতে পারে নমিনাল। নমিনাল মানে আমি জানি না, আই কালার মডেল করতে পারে ফ্রম অ্যানসেস্ট্রাল history. সেখানে it's a categorical total category, but it's nominal. সেই modeling frameworkটা will be different from a categorical variable that is ordinal, meaning like cancer stage, local, regional, distance. If 1, 2, 3 নয়, ordinally. So we can capitalize on that inherent ordinality and we can model it. In this general class, but there are different names for that. For example, a nominal outcome entry, what is called a polytomous solution. Dichotomous is what is polytomous. কিন্তু অর্ডিনাল ক্যাটেগরিক্যাল যেটা সেটা সেখানে একটা এক ধরনের মডেল এক্সটেনশন অফ দিস সলিউশন, বাট ইটস কল্ড দ্য প্রপোর্শনাল odds মডেল। প্রপোর্শনাল odds ব্যাপারটা কি, ওই it's not 1, 2, 3 the cancer state, but we expect on an average people with regional disease have a higher odds of what's outcome survival, let's say 2-year survival than people with sorry, I'm model করছি states হচ্ছে outcome, হ্যাঁ। তো আমি ধরে নিচ্ছি যে ওই ডিসটেন্সটা ইজ ওয়ার্স, রাইট? কিন্তু সেখানে একটা অর্ডিনালিটি আছে, we utilize that ordinality. It will fall in this general framework, but there are variations. So the statistic is also essential. Yes, I mean statistics again inference ইত্যাদি সব একই রকম, কিন্তু the interpretation fraction becomes very.
Okay. So this allows us to consider multiple predictors simultaneously, adjust for confounders. And here is the interpretation. So the model is like this. আর beta 1 যেটা ওই linear মডেলের স্লোপ বলি আমরা, সেটা এখন চেঞ্জ করে তার ইন্টারপ্রিটেশন হয়ে গেছে ইটস দ্য চেঞ্জ in the log of the odds for a 1 unit change in x. But this is not an odds ratio. Because simple example যদি ধরা হয় যে x is a binary predictor, if x is 0 তাহলে log odds টা কি? log odds ওই ইকুয়েশন x equal to 0 বসালে আমি পাচ্ছি beta 0, right? x equal to 1 বসালে আমি log odds টা পাচ্ছি beta 0 plus beta 1. So if you take the difference between x equal to 1 versus x equal to 0, the difference in the log odds, you get back beta 1. So beta 1 এর interpretation ওই যেটা slope ছিল linear regression এ, সেই beta 1 এর interpretation এখন হচ্ছে it's the difference in the log odds between x equal to 1 and x equal to 0. আপনি জিজ্ঞেস করছিলেন কেন log e? এবার এটাকে যদি আমি এক্সপোনেনশিয়াল, কারণ ওই এক্সপোনেনশিয়াল শেপটা দেখেছিলাম বলে আমি ওই log e নিয়েছিলাম so that I make it almost linear. এবার এই beta 1 টার interpretation হচ্ছে it's the difference in the log odds তো. So now if I exponentiate it, oh I'm sorry, you should have told me
I
earlier.
just
Oh, I'm sorry, why didn't you speak up? Yes, you should have told me.
online audience.
Okay,
They have
okay,
joined.
okay. I'm really sorry for the people who were online, and when I was speaking in Bengali, I didn't know there are people non-Bengali speakers in the audience. Thank you for joining, but again, you should have told me earlier. So anyway, we'll so basically what is happening is now beta 1 is the change in the log of the odds for a 1 unit change in x. And now, as you can see, the reason why we take the natural logarithm log base e is because beta 1 is the difference in the log odds. And now what can I do? A simple trick. I take the exponential of beta 1. What happens if I take the exponential of beta 1? We all learned in high school math, right? Log A base E minus log B base E is equal to log A by B. High school algebra. So now if I take the exponential, what happens? I get log of the ratio of two odds. And there's a name for that. We call it odds ratio. Okay, so now if I exponentiate, again, back in the day math class, I miss it. I had a brilliant mathematics teacher in Pathu Bhavan who basically inspired me to go to ISI. All I loved was mathematics. So I actually owe it to him for my career. So anyway, so this is the ratio of the two odds in the log scale. If I exponentiate, then I get back the log of the odds ratio is beta 1, and therefore beta 1, how do I get back the odds ratio? It's exponential of beta 1. Isn't that beautiful? Right? So again, I'm just trying to make the point here that I mean, behind there is a lot of math, but like conceptually, we should all be very clear why we do certain things. So the key point is to get the odds ratio, we have to exponentiate the coefficient, and that's what gives us the point estimate. So CHD and hypertension. Suppose we fit a logistic regression model, and we on the log of the odds of CHD is equal to beta naught plus beta 1 times hypertension. Hypertension is a binary predictor. So there is also another name we give to this. It's called the indicator variable or a dummy variable. So remember the weight category that we had. So we could actually break up that weight category into, there were 4 weight categories. So we could break it up into, remember I said you can break it up into 3 2x2 tables. So you can create indicator variables or dummy variables. So this is another concept that comes from linear regression. And so the exponential of beta 1 is the odds ratio comparing the hypertensives to the non-hypertensives. And lo and behold, from the what you got from the 2x2 table, now the odds ratio from the logistic regression, you get exactly the same, 1.9. Right? Okay, so again, what's the interpretation of the 0.9? So hypertensives have a 1.9 higher odds of coronary heart disease compared to the non-hypertensives. So again, this is basically doing the same thing in SPSS. Again, that practical note, be very careful in how you are coding the dependent variable, because you want the disease to be coded as 1. Number of patients, coding for dependent variable, always double check that yes is coded as 1. And here from the 2x2 results, you got a 1.91. And from logistic regression, you got a negative 2.93. You exponentiate that, you get a 0.652. This is the coefficient, beta 1. This is my beta 0. Constant means like the intercept in the linear regression model. So 0.652, you exponentiate to get 1.91. So this number matches this number exactly. But now the additional advantage is you also get the confidence interval, 95% confidence interval. So what's the conclusion? The conclusion is that there's a significant association between hypertension and the odds of developing a CHD. The odds of CHD are 1.91 times higher among hypertensives than non-hypertensives, and the 95% confidence interval is 1.45 to 2.53. So a pretty strong evidence of association between hypertension and CHD, and the conclusion is same as before. So I don't know, like you tell me, like should we stop? But can I just say a few things before we take a breath? So the next sort of example I had was, remember how we did the 2x(k) table with weight category. So we could do the same analysis now using a logistic regression model with the weight categories. And the way I'm going to bring in the weight categories is I'm going to fit a logistic regression model, again, a model of the log odds as a function of beta naught is my constant. And then now, do you see I have 3 different coefficients? Why 3? Because that weight category had 4 levels. I made the less than 140 pounds my reference group. So I have 140 to 170 versus less than 140. That's my beta 1. I have 170 to 200 compared to the less than 140. That's my beta 2. And I have above 200 pounds compared to less than 140. That's my beta 3. Got it? So what I was saying in the 2 by K table context, that you can break that table up into 3 2 by 2 tables. Basically, you are doing that in logistic regression in one stroke. So, and again, you can carry on through the inference exactly the same way, and you exponentiate the coefficients to get the odd ratios. You verify the coding, all of that. So ultimately, the inference is, again, there's a statistically significant association between weight and CHD. And just like we found that the 140 to 170 pounds group is basically not significantly different than the less than 140 pounds. It was the odds ratio was 0.98. And here you see the confidence interval is 0.56 to 1.73. So what did we talk about? That if the confidence interval contains 1, then there's no significant association. There's no significant difference here between 140 to 170 pounds versus less than 140 pounds in the odds of CHD. So we get all of that. So this example was to demonstrate that in the predictor space, you can have binary variables, you can have categorical variables like this. Actually, you can also have continuous variables like BMI. BMI is most of the times done as a BMI category, but age, let's say, age continuous age. So the right hand side of the equation can be any measurement scale. It doesn't have to be. So that's where I will stop and we will take a lunch break. And you tell me what we do after lunch. And because there were a lot of concepts here that we got to talk about. How to test for confounding, not test for confounding, how to assess confounding, how to test for effect modification, and then how to talk about prediction accuracy. I mean, I think many of you have worked with sensitivity, specificity, and like AUC, ROC curve. So, so there's a lot still left here, but I'm open. Like once we come back from the break, either we can talk about those things or we can sort of have an open-ended sort of discussion. Okay, does that?
One point I want to that like whenever we are planning our studies for our students also, whenever we open the sample size calculator, like I discussed, so there are different segments. Study which is assessing, which is being assessed by this, study which is being assessed by that, and then we are a bit confused as to which filter to apply and how what are the parameters so that we can get a appropriate sample size. So like if we can discuss about sample size calculation.
Those two are the basic, like
Very
what
useful.
type of studies and
Study design and sample size.
So we can come back and talk about study design. Sample size is $1 million question. Okay, because why is it $1 million question? Because again, I am my whole sort of my philosophy is for you to appreciate that statistics is not about pressing some buttons in a software. So if you tell me like which button I press, I'll tell you, sorry, I'm not going to tell you that. Because there's no one single answer to it. But what I can tell you is these are the things you should think about. So I cannot I can tell you, Dr. Sinha, I can tell you what you should think about. Like what are the sort of is it only the power? Or is it, for example, again, here is the so the when you are in the regression context, oftentimes if you are trying to design your study and your $1 million question is how many should I patients should I reach, right?
So the statistician, what we will ask you some questions, like what is the prevalence of the disease in the population? That's kind of your baseline. So you have to tell me that then I'll tell you what is a clinically meaningful difference. Sorry. That is something that if someone comes and tells me, oh, you tell me. I will say, no, you have to tell me because what is clinically meaningful? Like for certain diseases, a 1.2 odds ratio is remarkable. I mean, actually, I work with like cardiac physicians. So it's like, the mortality they have, I mean, medical technology and everything. There have been a lot of advances in mortality. But when it comes to morbidity outcome, we still have a lot to do, right? As you almost. So it's like the clinical significance is something that you have to tell you. Then I can tell you, well, in order for you to detect the clinically significant, like a meaningful difference of 1.2 or 1.4, be it 80% power, you will need to recruit these many patients. Now, the reason why I'm saying is I cannot give you one answer to that question, but I can tell you what you need. Now, think about time to event data. Oftentimes, what people miss is that for time to event data, like time to death, time to recurrence, it's not just the total sample size. It's not just the n that determines power. It's the any guesses? The other guesses. So the sample size calculation here.
When should be happening?
Incidence of events.
Incidence of events. How many events? So the statistician will come and ask you. So can you tell me what is the event rate, baseline event rate in the population? So the sort of the requirements, and this is where the clinician and the biostatistician works as a team, as a scientific team. Then we basically say, well, the event rate, and again, depending on, we talked about rare disease rate. So depending on if it's a very rare event, right from the get-go, that for example, very large. We get the same kind of hazard ratio. In the context of time to get data, we talk about the hazard ratio, not the odds ratio, because the outcome now is the time to get. So there are like, without kind of trying to sound like arrogant, I want to tell you that I really cannot give you one answer that satisfies everybody's question. It has to be like, you have to understand the sort of the setup, the objectives, and so on. So sometimes, and again, this is sorry, I know we have to stop, but I can't resist talking about it. So, so sometimes what happens is, you cannot even, I don't know, do you use any sample size software? Like, do you use?
Like the basic ones, PS, power and sample size calculation.
Okay. So
many things are available online.
Yeah, so there is a PASS software, there is an enquiry software. Actually, SAS also does that. But there are certain situations where you actually cannot, click a certain option from a drop-down menu and calculate sample size. Because analytically, we call that there is no closed form equation. So you cannot, like, the parameters to get the sample size, you cannot write n as a closed form function of, power, alpha level, prevalence, because it's not a nice looking closed form equation. There, what we do, we do simulations, Monte Carlo simulations, meaning what? You try to sort of simulate the
the disease process. So there you have the flexibility of kind of generating data, assuming the things that you told me. So what the statistician, biostatistician does, someone like me, they would go back and they would simulate the disease process. Okay, these are variables that underlie the mechanism of the disease progression or disease. So I bring in various variables, I bring in some distributions, I vary, and I simulate as if the disease, the data or the under which the disease has happened. And then I calculate power. So sometimes it's not even possible to get power from this software. And the reason why I'm saying is that before you even know how to, you have to understand what are the inputs, what are the things that I need to know, like a physical scientist knows from a clinical scientist, and where is it that we basically consider. Okay, so we can talk about study design when we come back and sort of more on this. Okay, sounds good.
It was already mute.
Was it?
I mean, it's crossed. It's crossed. I don't know. Or maybe they might have muted from there. I don't know, because it is being controlled from there also. Possibly. Yes. No, I mean, when I opened the Zoom screen, I found that it is mute. এখন করেছে I think it has been muted now. একদম একদম yes ঠিক muted, so no issues.
We will come back what time?
After lunch, maybe after around 40 minutes. That
So
around 3.
and then we will go till. I'm just asking because Peter is going to go our friend
Sure.
for just an hour.
No problem.
So, or maybe, and depending on when we are finishing, she will come back because I would like her to be there at the end.
Absolutely. No.
We have certificates.
Sure. We have e-certificates actually. No? Okay, we have got printed certificates. Okay.
You want the distribution? I think for those who
At
want
least
to
a
be present.
few.
Yes,
Yeah,
yes,
because
definitely.
then it's kind of a document for us.
Absolutely.
So what, till what time would we go?
Should we go till 4:30 or 4? 4:30. 4:30.
Are you okay with it? And it's been very long.
Okay, thank you.
I'm standing on the ladder. Maybe we'll have a chair.
Yes, that's fine. So 30, so Kiran, then yeah. Is that fine? Yeah. Yeah, so she's my sister. So she'll take Kiran and again because Kiran didn't get to do any shopping or
Sure.
anything.
Oh, okay.
So and come back by 4 because I want Kiran to be here when we are finishing up. So okay. Fine. Yeah. Did you want some?
I will start it. You can carry your lunch if you're short of time. Carry.
I'm going to go to
That
the
packed lunch will
restroom.
be available inside the director's room. Please come. Please come.
I will let I will go to the restroom. So we have questions.
तो फिर ऐसे में लेकिन हम सीखी
feedback. আবার চেম্বার করতে হবে এটা মিনিমাইজ করে ব্যাকগ্রাউন্ডে আছে তবে যখন আমি যাবো মিনিমাইজ করতে এটা করলে ওটা তাহলে এইটার কোনো দরকার না এটা ডাউনলোড হয় আসলে কি ওনার রিসার্চ করে ওরা ওনার কি হয় ওনার আর্টিকেল পেপার মানে জার্নাল করার আগে আপনার স্টাডি হয়ে আমার ইয়ে থেকে সেটার জার্নাল significance activity. Financial consultant মানে একটা তো আপনার একাডেমিক্যাল জার্নাল আর একটা ফিনান্সিয়াল হচ্ছে টাইপ ফিজিক্যাল পার্ট পেশেন্ট রিসার্চ করতে তাই মানে এরকম টাইম 500 টাকা সেখানে 10টা সাইট আইসি তাহলে পার্ট সাইট আমার 50 তাহলে 500 টাকা একই হবে তাতে আমাকে কিছু ডায়ালিসিস টাইপ ডায়ালিসিস দেবে একটা কোন কারণে এথিক্স টা কত আছে 50% এন্ড পয়েন্ট তো এটাই আপনি পাঁচটা এক একটা পেশেন্টের মধ্যে আপনার পেশেন্ট রিক্রুট করতে পারছেন ভিজিট হবে ধরুন পেশেন্ট যদি 5টা করে ফার্স্ট ক্রাইটেরিয়া থেকে ক্রাইটেরিয়া দেখে আমি পেশেন্টকে চুজ করবো একটা এজ রেঞ্জ আমি এই চাই বা প্যারামিটারস থেকে ল্যাব রিকোয়েস্ট সেখানে ল্যাব হোয়াইট ব্লাড সেল মারাত্মক একটা ক্যান্সারাস হয় বা অন্য ট্রিটমেন্টে এক্সাম্পল থাকবে সেই জন্য আমি ট্রিটমেন্ট করবো করে এবার আমি সেকেন্ড বেস লাইন সেকেন্ড আমি মেডিসিনটা দিলাম মেডিসিনও ধরো লাইক হ্যাঁ এগুলো দুটো ড্রাগ হবে একটা রেফারেন্স একটা কেস থাকবে একদম আর প্লাসিবো হ্যাঁ পারফেক্ট এবং বেস্ট স্টুডেন্ট যদি হ্যাঁ জিএসকে স্টাডি হয় বড় বড় জিএসকে স্টাডি বা ধরুন অ্যাবাউট স্টাডি মানে বিদেশি কোম্পানির মধ্যে খুবই ভালো লাগে ইন্ডিয়ান কোম্পানিও ভালো দেয় ভালো খারাপ পারমিশন দেয় এবং ইসিসিএল মানে করেছে ইনস্টিটিউটে দেয় হ্যাঁ হ্যাঁ ভালো পায় বিশেষ করে পারমিশন এই ইসিসিস দিতে হয় এবং সিনপসিস অফ প্রোটোকল এথিক্স রেগুলেটরি যদি হয় তো পারমিশন লাগে আর এটা যদি ফরেন হয় তাহলে ইউএসএ নার্সিং ইউনিভার্সিটি এমবিএ আমি আপাতত কেন CSI এর আবুল থেকে গেছে টপিক্যাল এসে থাকতে পারে ভালো স্ট্যাটস স্ট্যাটসটা এই আরের একটা প্রোগ্রামিং ল্যাঙ্গুয়েজ আপনার আরের কেউ বাউন্ডারি আছে আর পার্ট ফ্রি সব স্যাস প্রোগ্রামিংটা এখন প্রিফারেন্স সব কটা প্রিফারেন্স অটোমেটিক লাইক ইয়া অ্যারে বড় বড় যাওয়া এমএনসি প্রত্যেকে স্যাস ইউজ স্যাস শুনি এসপিএসএস ভালো ইউজার বাট এসপিএস করা যায় আরে করা যায় আর প্রোগ্রামিং স্যাস এখন শুনি স্যাসটা একটু আরো বেশি 1.5 লাখ টাকা 1.5 লাখ টাকা খরচা যায়
সুরজিৎ আমি মিউট করে রেখেছি, আনমিউট কর।
ঠিক আছে পরে একটা দেখিস পরে
হ্যাঁ, কারণ হচ্ছে
আর ওপেন সোর্স এখানে স্যাস প্রপার্টিজ অফ ডেটা এটা মানে তাহলে স্যাস সেটার জন্য ইউএস স্টুডেন্টদের অনেক বেনিফিট হয়েছে যে স্যাস
মানে ইউনিভার্সিটি মাস্টার স্টুডেন্টদের পছন্দ হয় না ইউনিভার্সিটি
স্যাসও মানে ইউএস স্টুডেন্টদের জন্য অনেক অফার টফার প্রোভাইড করে যেটা ইন্ডিয়ান স্যাস করে না। এই একটা সমস্যা।
আর মানে তারপরে আর
আরে আপনার আমাদের বায়ো ইনফরমেটিক্স বলে একটা মানে বায়ো কন্ডাক্টর প্যাকেজেস
হ্যাঁ।
কেস আর এগুলো সব করা যায়
সব করা যায় না। আরেকটা রিসার্চ সফটওয়্যার তো যেটা হচ্ছে আমি টেকনোলজি থিওরি ডেভেলপ এবার সেটাকে আমি কোড করছি সেটা আমি আরে পজিটিভ
র্যান্ডম ফরেস্ট যেটা অনেক পাথওয়ে
and sort of depositing plan.
মডেলগুলো সবকটা কনসেপ্ট করা জাস্ট ভ্যালু who has the concept is just kids যার কনসেপ্ট শেষের তার কাছে একদম বাচ্চাদের যে জীবনে তৈরি করে সোলাইজেশন থেকে স্টার্ট ডেটা ম্যানেজমেন্ট
The enterprise, profitable enterprise. SAS not the kind of the the statistician employer. So obviously they have their own market strategy. Are they আমাদের ডিপার্টমেন্ট আমরা আর everybody writes our shiny apps. Everybody puts it as open source, right? Anybody can access. So, আজকে আমি যে there are two classes of statistics. একটা হচ্ছে ওই তারা কি থিওরিটিক্যাল ট্রেনিং দিয়েছে আমি theoretical বিদেশে যাই তো ফার্স্ট 6 sort of like applied science তো যেটা হয় যে এক ধরনের স্ট্যাটিস্টিক্স যারা থিওরি ডেভেলপ করে মেথড ডেভেলপ করে এবার তারা বলে লেটস ফাইন্ড দ্য ডেটা টু অ্যাপ্লাই সেখানে আমাদের পার্সিস্টেন্ট the science motivates my research, my methods. মানে আমি কখনোই মেথড ডেভেলপ দিয়ে ডেটা খুঁজবো না ডেটাটা আমাকে বলে দিতে দেখো এটা একটা ওপেন প্রবলেম এই হচ্ছে আমার ক্লিনিক্যাল সায়েন্স এখানে না মানে ফুড স্ট্যাটিস্টিক্যাল মেথডলজি নেই তো তোমার সেই নলেজ ডেভেলপ আমার মেথড আমি ডেভেলপ করছি মানে হাই ইম্প্যাক্ট স্ট্যাটিস্টিক্যাল জার্নালে পাবলিশ আমার টেনিওর পোর্শন হচ্ছে কিন্তু আমার মেথডটা যদি ইউজ করছে তো সেটা তো আমার মেইন উদ্দেশ্য কারণ না হলে ইচ্ছা করবে তো দ্যাটস ওয়াই I was like contribute seminar and so that it's widely. So at the end of the day, what only stays in a journal and what is using it, it's not making any impact in inference. Then for me, yes, I'm a full professor, that is, I do a paper now at my stage of my career. And আমার ছেলেমেয়েরা থাকতাম so I don't think that paper. So I need to do stuff that makes a difference. So সেই কারণে আমার কাছে we were talking about sort of programs that we develop. সেইগুলো economic the broad out. Right? So, so there is a difference. This SAS is the pharmaceutical company, তাদের পয়সা এবং তাদের কাছে their revenue generated. Whereas in the academic department, it's kind of sharing of ideas.
আমি কাজ করি সেখানে যে আপনার ক্যান্সার ভ্যালু নেক্সট জেনারেশন সিকোয়েন্সিং করে পাথওয়ে ইনভেস্টমেন্ট অ্যানালাইসিস
তার কারণ হচ্ছে অ্যাক্টিভ রিসার্চ হচ্ছে
এনআইভি
অ্যাক্টিভ রিসার্চ হচ্ছে repository so that everybody can follow the world. I think that is a real meaning for it. Because I don't want my work to now just be published and sit in one corner of the academic world unless it's used over to the so that's philosophical.
আচ্ছা আপনি যে অর্ধেক 1.91 তো বলছেন 1.9 চাই 91 চাই না কিন্তু এরকম বলা যায় যে 1.9 দেখি যে আমি এরকম বলি যে যদি এরকম পপুলেশনটা থাকে 0.1 পপুলেশন নাম্বার হচ্ছে 2 পপুলেশন স্যাম্পল সাইজ হচ্ছে 0.1 সেখানে 191 সাবজেক্টসে এই প্রবলেম আছে যে ওইটা আন্ডারে পড়ে একটা টেনশন আছে সিএইচপিও এনভায়রনমেন্ট
one size fits all type of answer. Then some we will talk one-on-one. Standard analysis of compared features. The finally outcome is the influences that now so you can reduce independence and then there are here. Okay. Actually, we were having some sort of side discussions. মানে আমি যেটা বুঝতে পারছি there is tremendous need here. এবং একটু প্রশ্ন হলো একজন জিজ্ঞেস করলেন আবার a very low prevalence disease, right? And sample size calculation. I actually I cannot give you like a one size fits all answer. It varies from design to design, study to study. And we need to have a one-on-one conversation. তুমি বলছি তোমার স্টাডির জন্য people are on the so for you we have to have a one-on-one conversation, right? So the other question that came up is I have pre-post data. How do I analyze? So again, pre-post data when there is when the outcome is continuous, you do a pair t-test, the univariate setting. When the outcome is binary, what is called a McNemar's test, and then there is a regression framework.
But again, that's something that I cannot, like we have to have a one-to-one conversation. So looks like there is tremendous needs. And unfortunately, as I mentioned, the 2 days is too short a time. It's not even, as we all know, like you spend like what, 5 years of your career, right? Getting your MBBS, CBS, and stuff, you have an MD, another 7 years. So similarly for students, like for someone like me, I had 3 years of bachelor's training at ISI, years of master's, and then 5 years of PhD, where I could become a professor, like an assistant professor. And then now I have been in the profession for, I'm old actually, for almost like 30 years, 30 years. I kind of went to the US when I was very young, but I have been doing this for 30 years. So it's like any other discipline. It's like it's sort of it takes a lot of hard work and learning, and so if I cannot, like, we all know nothing is easy, right? Everything is, you have to work. So it's basically like in 2 days I really cannot do justice, and we were talking about, we were having very good discussions about sort of going forward, thinking ahead, whether we could develop some programs on a longer term basis, where we sort of develop a more kind of streamlined, sustained program, and kind of a certificate program over a period of like a year, maybe, so that we can build up on. Like I said, if we had the 1 year where, like, maybe every 2 weeks we do sort of a lecture of about 4 hours online, then we could go through that sequence, develop, and I could tell you. So then the sample size question, the median error sample size question, for linear regression we talk about sample size. How? For logistic regression we talk about sample size, power. So it becomes a much more streamlined and complicated. So maybe, hopefully down the road, we might be able to develop something. But for now, I kind of want you to sort of appreciate that it's very important. So even if by the end of this workshop, if you go back with the understanding that, well, I'm now able to better interpret what I read in a clinical journal, I would say, I would be happy. I have achieved the goal. Because I'm not expecting you after today, suddenly tomorrow go and start, sit on a computer, write your codes and run the analysis, do all your sample size calculations. I'm not expecting that. I want you to, I'll tell you this story. I don't know if I told this story at PCI. So I teach a group of learners like you. Just like I teach in our master's and PhD programs, I also teach a group of learners like so the difference between the teaching style is very different for the students. When I teach the master's and PhD students biostatistics, I can write a lot of equations, write a lot of math, and I kind of resort to math to explaining all difficult concepts. When I'm teaching groups like you, I try not to write a single equation, but I try to focus on concepts and clear your interpretation understanding. So there's a program at the University of Michigan for learners just like you, who are really like all are accomplished in your own field. Many of you have been sort of doing clinical research for the last 30 years. right? And you know your field, you are high achievers. Nobody has forced you to come to my lecture and or they should. You came because of your motivation, your goal, right? So you have to have a very goal-oriented learning. And so there's a program at University of Michigan. It's called OJOB, On Job on Campus. So where physicians like you come, it's an 18-month program. It meets 1 weekend a month, Thursday to Sunday. And that's during that weekend, it's very intense. And at the end of the 18-month program, you get a degree in Masters in Clinical Research Design and Statistical Analysis. It's a Master of Science. So there, I mean, at the beginning of the first lecture, I tell everyone, please tell me a little bit about your background, what is your clinical subspecialty, collect that information so that I get a, just as I did for the workshop, that I get a sense of who my, who the audience is. So there was a year, I distinctly remember, so I got little notepad back, so I'm kind of hemong person, I done this, nephrology, pulmonology. So there was, I got a little notepad from someone, and it said, well, I have been in clinical research for the last 35 years. I am the director of the bone marrow transplant program at University of Michigan Cancer Center, and lots of other things. I've published, So the next day I go to lecture and I say, why are you here? I mean, you're here, right? Yes, sir, Dr. Sina, why are you here? So your career is made, you have seniority. You are the director of bone marrow transplant program. So he, very nice gentleman. So he looked at me, laughed, and the first thing he said is, because I want to get independent of people like you. every time I meet with people like you, I feel like you are so smart and I can't understand. And then then he said, no, what I mean is I am here because I want to have a more informed dialogue, conversation, collaboration. And I think that should be the goal. That sums it up. So I am not expecting you to go write your codes, but next time you design a new study and you are talking to a statistician, you know exactly, you know their language, they know your language. You can communicate better, you can express your needs. So that, because ultimately it's a collaboration. And again, statisticians generally, I'll tell you, they don't like it. Only come to them and ask like, tell me what the sample size I need. Because we are not sample size generally. We are scientific collaborators. So like, I cannot tell you like one answer to the sample size. So that, I think that's where it becomes a partnership. That's what we are. So I hope that sort of sums it up. And I think it's possible to do that within kind of a time frame that allows you, for example, like if you had time to kind of go back and sing and these concepts sing, then after 2 weeks you come back and we sort of take it up from there. It's a much more sort of, how do I say, the concepts kind of go in. There's a value to sort of learning that way, rather than, and again, basic. Okay, so now there was a, so we can do it as this session as more of an open discussion, and that's what we will do. So there was a request to talk about study designs, right? So I am going to go and so we are abandoning logistic regression And we are going to go into talking about study design.
Just one small thing. So, in the example that you were giving about like BMI, weight also, BMI,
Weight category.
heart disease increase.
Yeah.
So, and you showed that like for a weight, whatever, you said that in this weight range, odd ratio is this weight range, odd ratio is this, and in this weight range, odd ratio is this. If I want to show that as your weight increases, your CHD increases, what do I use that?
Okay, so the great question, and actually I had a slide like that in the logistic regression. Okay, let me just tell you in words. So what I did, if everybody remembers, I created 3 indicator variables from that weight category, and for each of those, the reference was the less than 140. So what Dr. Sinha is asking is that inference is saying, well, is there a difference between the 140 to 170 versus the less? So that there was. Is there a difference between the 172 versus the less than? So there was. Right? And then same with above. But what Dr. Shiva is asking is, can I say that as weight increases, the odds of CHD also increase, right? So there are 2 ways you can do that. You might say, and you know better than me, you might say, well, you know what? Although I want to investigate that question, but I think a weight difference of like 4 or 5 pounds wouldn't make a difference. So, like if I have like someone 140 versus someone 142 pounds, wouldn't make a difference. Or 145 and 147 pounds wouldn't make a difference. So what the point that I'm trying to make is 1 unit increase, 1 pound increase in weight probably wouldn't make a difference in the CHD risk. So instead of the disk increasing linearly, that is it. Okay, and here is this, or I actually pause. Instead of that, relationship between be almost kind of linear, okay? And actually I'm going to make it draw on that. So instead of the relation between like this, again this is hypothetical. Maybe, so this is where weight is continuous. Weight in pounds, continuous. Maybe it's more like a step function, it's a threshold. But maybe the relationship like slips downwards. And here are the weight categories. Again, the less than 140, so here I have weight categories. Okay, but instead of making the weight categories like how I analyze it, as if it's nominal, I am going to say if the value 1, the less than 140, 140 170, I give the value 170, 100, I give the value 3, and then above 100, I give the value 4. So I have created a new variable with values 1, 2, 3, 4. I model with respect to that. So then what happens? How does the relationship apply? It's basically like a step function. So this is, let's say, 140, this is 140, 70, 170, 100, and then this is above. So I say, well, less than 140, in that group, the odds is constant because a person is like 139 versus 140 or 114 versus 140 doesn't matter. But the 140 to 17 has a higher odds, but again we the 140 to 17 second fact. And then once after higher odds of CHP and above 200 is there. So do you see it's like a step function? So it stays same in that category, but there is an increase going from one category to another. So if Dr. Sinha, if I model this now as a 1, 2, 3, 4, if I model this as a variable, like a continuous variable, but with the values 1, 2, 3, 4, then I will get the inference. Did that make sense?
Then this once you move step by step and find out if the
Yeah.
difference is
So not only that, no, but there is a restriction now I'm in place of compared to that one. By making it 1, 2, 3, 4, I am saying that's why I do the steps like this. That the spacings are the same. Going from this to this, the spacing of the jump is going to be the same as the jump from going from this to this. Jump going from this to this. So do you understand that I have this model is not going to be the same as the model I did? Because there I have kept it completely flexible. The jump could go any way. Here by making it 1, 2, 3, 4, so there's equal spacing between the 1, 2, 3, 3 to 4. So I'm saying the size of the steps, size of the jump has to be the same. So this is what is also called proportional odds. So, without going too much into the technical details, there, when I was making inference about the weight as a categorical variable, because I was using 3 dummy variables, so we statisticians call it 3 degrees of freedom, because those odds ratios could vary in any way. Here, if I model this as a variable that takes value 1, 2, 3, 4 for those 4 categories, I use only 1 degree of freedom because the minute I estimate that one parameter, that one coefficient, I'm saying going from category 1 to category 2 has the same sort of odds associated going from 2 to 3 or 3 to 4. So that's the difference. Make sense? So you can see like the way you analyze, and again, how do you sort of understand which one to fit, which model better describes your data? That's where, again, sort of looking at the graphical displays You can also formally test for which is the better model fit, all of this. Yes. Okay. So now, uh, yeah, so we have to start from here. Okay.
Can we circulate it to the,
Yeah, we want to pass it
I
around.
just asked.
Oh, you did? Yeah. So please, um, the feedback, evaluation that will help us. I don't hear that by tomorrow night. Ask me for the electric version. Should work with, yeah. Some kind of, yeah. So the, if you take a picture, I don't think the hyperlink
No,
will show. Yeah. Yeah. So I can email you the hyperlink. No. Yeah, just no. Okay. So we will spend some time talking about study design taxonomy on popular demand. So two broad classifications: observational studies versus experimental or controlled studies, I should say. Because the intervention be a natural intervention, and that can be sort of social shock the system. So that can some policy change, right? So that can be part of an observational study. So when I say experimental or intervention studies, I mean controlled experiment studies. So in observational studies, the exposures occur naturally. In experimental studies, the investigator controls the treatment allocation and the exposures.
And sorry, a very basic question.
Sure.
And both of them can be retrospective and prospective.
Typically, yes, both of them can be retrospective and prospective, but typically controlled trials are prospective.
Can we have a control?
Experimental studies are typically prospective.
Can we have a control study which is retrospective? By design.
By design,
Suppose if I want to look at like some procedure,
yeah.
so how do I and then retrospectively looking at it? So that is not occurring natural. Say a cardiac stenting, and
Yeah.
whether it is live.
Yeah,
So that is an experiment for intervention because it's
No,
not
it's-
happening naturally as your
yeah, no, that's why I said the word intervention probably has to take it like as if it's a controlled um, allocation of a treatment. So same thing, you cannot do it in a control, right? It is sort of gets it. If there's a drug, for example, that you want to give to randomize and give to a certain group of subjects, and the other group you give placebo, that is an example of a controlled
that
study.
is experiment.
Experimental, and when you are actually allocating the treatment, you are allocating the treatment. Got it? So the same thing example, you are not allocating. If I mean ethically you cannot, right? So you
So then
cannot.
that will also fall under observation.
That will also fall into observation.
Also it's not natural.
Although it's not naturally, but in a way, I mean, how you
can say
interpret
that
the word naturally.
natural evolution of the
Exactly. How you interpret the word naturally. Yeah, yeah. So you can interpret the word naturally because it is not controlled by the investigator. Like ethically, you cannot do that, right? I mean, ethically, you cannot say I want to randomize stent. Pretty much all drug trials are controlled, experimental trials. And pretty much all sort of studies that look at the natural progression of disease are observational. Okay? So now, oh, what happened? Okay, so now observational studies are used when intervention is not possible. Again, I think the word intervention might throw people off. Meaning that when you cannot, it happens naturally. Whatever the exposure is, whatever the intervention is, happens naturally. This is a very powerful tool for studying etiology of the disease. Risk factors, association studies, causal studies, causation are essentially fall under observational studies. There are two basic designs, the cohort design and the case control design. So under observational studies, these are the basic designs, and this is what we were talking about. Most of you, if you are analyzing data, which I think mentioned that you have registry, is registry, but analyzing data from the disease registry. That's an example of an observational study. And most likely, of course, to collect the data prospectively, follow up those people over time. So it's a cohort, example of an observational cohort. What about a case control study? So the case control study is where study information is obtained retrospectively. So you study kind of begins here.
So case control cannot be prospective.
Case control, there are some more recent designs where there are cohort within case control studies. The cohort part is the prospective part, but typically case control classical design cannot be. Make sense? Case control studies, okay, there is one other thing. Case control studies, because of the nature of the design, the reason why people in epidemiologic studies, there are a lot of case control studies is because cost-wise, they are less expensive than cohort studies. Cohort studies can become prohibitively expensive, for the same sort of evidence to emerge, because you're following up some diseases may take many years to develop.
So suppose, sorry, being back.
Yeah.
Suppose they decide that I'm just making it up that I will for a cardiac something, I will stay in that group and I will not stay in another, and I don't do any randomized.
No. Yeah. You like you cannot allocate. Can you allocate who gets stent and who doesn't get stent? You cannot randomly allocate. Can you randomly allocate? No. Why is the random allocation important? Because of the key point that I was making, that in control studies, the reason why the random allocation is important, because you are saying that, everything else about the patients in the stent versus no stent group, I have made equal.
I'm still a bit confused.
Yeah.
Not a bit confused.
Okay.
Suppose I am working in a center.
Yeah.
Say disease A.
Disease A.
And there is an intervention for that. So I am working in a center where that intervention is available.
Yeah.
And she is working in a center where that intervention is not available. Then but that's it. And they decide that that we will compare that. For example, there is a drug called eculizumab, which is useful in hemolytic uremic syndrome. It is available in India and it is not available. Sorry, it is not available in India, but it is available in US. And they decide that over the next 5 years, we will collect the data, both of us, and we will compare. Will that be a case control?
Oh, you are talking about case control or
Case control.
or observational
No.
versus experiment?
That will be observational, but case control study.
So they have the disease already.
We have a disease, HUS,
Yeah.
and we have a treatment which is available in her country, but not in my country.
Yeah, but everybody has the disease, right? In her country also and your.
Yeah.
No, that's.
So we decide in the next 5 years,
Yeah.
we will see in her country she gives eculizumab. In my country, I don't give eculizumab, and we see the outcome. Will that be a case control?
No, that's a prospective study.
Why? So
That's
why
a
not case control? Because like I may get a question, but I'm just asking. Why not be thinking that I'm not giving the medication? So I consider myself as a control, and she's giving the medication. She
No.
So, other here I
on
can
the
take,
disease.
so rather I can take the giving the medicine as exposure.
Exactly.
And then I see the outcome.
Exactly. Yeah. Yeah.
That is not case control.
No, that is not case control because everybody is a case.
Everybody okay.
Because
So the
everybody
control,
has disease.
control has to be someone who is not having that.
Exactly. Exactly. Everybody is a case according to your sort of scenario. Case control studies are very standard epidemiologic studies to understand the etiology of or the progression of a disease or kind of association. Like, does smoking cause lung cancer? Okay, so what do you do? Like a case control study, the way it will happen is the study will begin by selecting a group of lung cancer patients and selecting a group of non-lung cancer patients. So the non-lung cancer patients are my control. And again, there are many issues like how do you, they're not having that disease, the non-diseased.
As a control, I have to take patients. Can I take normal persons?
Yeah, that's what I was coming to. So how do you select the controls is sort of
non-cats. That means are they having another disease or they are not?
Okay, so that's where I was coming. So the selection of the controls is an important consideration. There also, there may be some studies where actually you are saying that case control is where I'm trying to sometimes people might do kind of in a stratified way. So I will select cancer, lung cancer patient as my like disease group and my or my case group, and my controls I can either select non-lung cancer that will give one kind of difference, or I can select healthy
Or
participants.
not lung cancer, but another type.
Yeah, all I'm saying is that depending on the selection of your control group, the inference or the conclusions will be different.
Selection bias.
There will be selection bias. So, like if you take, let's say, if you take generally the sort of the standard would be to take for smoking would be to take healthy, right? Because then you are saying that in the healthy population, even among smokers versus non-smokers, I know that there is a baseline difference. Okay. But do I see that difference attenuated in the lung cancer group? And that's what the inference is based on. Okay, so the design is the study begins by actually first kind of fixing your cases and controls. And then you kind of go back in time. Study information is obtained retrospectively. So among the diseased and the control cases, you look at the exposed versus the non-exposed. Exposed meaning like smokers, non-smokers. So there are four, and here is time. Time is going prospectively, but your study information you are getting retrospectively. Okay. So this is a classic case control design. Now, why case control designs are so popular in epidemiology study? These kind of designs are best for rare diseases. Why? Because it may take a long time for the disease to develop. If you do a cohort study, if you're following up, you might have to wait for 10 years, 15 years, 20 years for the event to happen, for the disease to develop. So this is one way, this is economically much more kind of feasible design that it essentially allows you to still study the etiology or progression of a disease based on, retrospective information on the exposures. Concerns, as you already just pointed out, and this is the point that I was going to make, but you already asked that question. The selection of the controls is important. And there could be selection biases if you do not choose the controls carefully. Okay. And again, as you can imagine, this will vary from disease to disease. This will vary from sort of your primary scientific question. But the selection of controls is extremely important because you could get into selection bias if you choose your control group.
Case control always has to be retrospective.
Yes.
Cohort studies can be retrospective.
Yes, but cohort studies again are typically prospective. Cohort studies are typically prospective.
Always.
Not always.
Not always, but that's kind of the standard. ওটা প্রসপেক্টিভ একদম, কারণ আউটকামটা তো ইভলভ করছে তাহলে হ্যাঁ ওটা তো আউটকামটা তো ইভলভ করছে।
ওখানে আরেকটা আছে, যেমন আমরা ডক্টর সঞ্জুক্তা একটা স্টাডি হচ্ছে, সেখানে আমাদের একটা এসএবি ট্রেনিং আছে, সেটা অনেকদিন থেকে চলছে। তো আমরা দেখছি যে এই এসএবি ট্রেনিং যারাই পেশেন্ট আসে তাদের আমরা কার্ডিওভাস্কুলার মরবিডিটিটা দেখি, কিন্তু বয়স পাই। তো এটা কি দেখছে?
Now, then what is your question?
that SAD cohort cardiovascular
Incidence study.
prevalence.
Yeah, it's a prospective study. It's a very descriptive study, right? There is no inference.
Why is the prospective study? Because আমরা তো
You're following up, no?
আমরা তো
You're following
বাচ্চাকে ফলো করছি না,
তাহলে
জাস্ট মানে আমাদের যে ক্লিনিক চলছে সেই ক্লিনিকে মানে অনেকদিন থেকে বাচ্চারা আসছে, আমরা কোনো এক পয়েন্টে ট্রেনিং আমরা ডিসাইড করলাম যে আজ থেকে যে বাচ্চাই আসবে তাদেরকে আমরা কার্ডিওভাস্কুলার মবিলিটি দেব।
মানে specific time follow that there are certain cardiovascular markers that we see that
So that's a 40 studies is right.
yeah.
but we will not be follow because the
No, I know you are not doing follow up, but your data collection is prospective, futuristic, right? Because you are not going back in time to get their information. Yeah, so the data collection is happening prospectively. And for you, that is more of it's a very descriptive study, right? You are not doing any inferential thing. So, but the data collection is happening prospectively.
আর এখানে ক্রস সেকশনালটা কোথায় আছে?
Acha, cross-sectional is a different thing. Cross-sectional is in a single point in time that you are saying you are measuring
You
something.
don't have a denominator.
তাহলে আমাদের স্টাডিটা কি ক্রস সেকশনাল
Yes.
প্রসপেক্টিভ স্টাডি?
Cross-sectional prospective, actually, in your case, they will say cross-sectional prospective survey.
But as because the denominator, there is no population denominator, how can you call it an incidence?
No, that's not an
Incidence
incidence.
assessment.
Yeah, no, but that's why I said they're doing
Proportion.
they're doing a descriptive study, prevalence. That's it. So prevalent in their population. So that's the so these terminologies can throw off people, but just the thing to keep in mind is how is the data collection going? Like, is it going kind of forward in time or is it backward in time? For case control designs, the exposure information you are collecting backward from time. The other thing that the other concern about case control studies is yes, information bias, recollection bias. People may not be able to remember whether what they did, like 20 years back. So there are, and there may be differential information sources for cases and controls. People, I'm just making it up. Don't laugh if this doesn't make sense clinically. So for normal healthy controls, they may not, even if the smokers kind of gave up smoking, they may not remember when, But for a person who was diagnosed of cancer, for them, the recall bias, they will remember, I smoked like 40 years and X many packs of cigarettes. So there could be a differential bias, recall bias between the cases and control. So that's the biggest sort of con about case control design. But as I said, these are comparatively, relatively cheaper studies, require less money, and again for rare diseases, probably only source. So here is an example of a case control study. The smoking histories of a sample of 1357 male patients with lung cancer cases and of an age-matched sample of 1357 normal males, controls are recorded. So I have again a 2x2 table, right? So lung cancer cases versus controls. And now I retrospectively went in time to collect information about their smoking. So in the 2x2 table, 500 of the lung cancer cases did not smoke cigarettes, but 857 smoked cigarettes. For the controls, 900 did not smoke cigarettes and 457 did smoke cigarettes. So again, how would I estimate the risk of lung cancer? So I can do it again. I can calculate a odds ratio. I can calculate like a risk difference. And the risk of lung cancer estimated here it was 2.34 times greater for the smokers than for non-smokers. Okay, so now, yeah.
Our studies like or incidents and prevalence. Right? Institution-based studies can for prevalence of
Prevalence you still can, because you can say the prevalence of disease in your population.
this will be an institution for my
Yeah. But prevalence is just kind of think of it as the proportion of cases subjects with the disease at that point in time. That incidence is a harder thing to estimate, because you are saying what is the number of new cases of the disease.
during my thesis time, like for 2 years, I'm
Again, incidence is generally reported in terms of like the general population. So you have to fix your population. So there are, as long as you understand what you are estimating and you interpret it correctly, but the nuance is that incidence is always about new cases.
incidence and prevalence are mostly population based.
Yes.
But again, the sample size is quite large. Based, or it is
No, you can, that's what I'm saying, that you can say the prevalence in my institution, but you cannot generalize it to the population.
But in my study,
Not in your study, because it's about the population you are studying. The population you are studying is your hospital. But you cannot generalize it to the larger population.
So can we say that the prevalence was so and so in this study that was carried out in ICH? When we use a title like that, this is the
No.
prevalence.
I mean, you again, as long as you prevalence is a probability, is a proportion. As long as you are reporting for your institution, you can. But with the disclaimer that you cannot generalize it.
And if you cannot generalize it, you cannot do the statistical analysis also.
Well, there are single institution studies that are done all the time.
Statistical significance will be different.
No, the thing is that there are lots of single institution studies. So, you know, and they are published, but the idea is your institution representative of a set of large institutions in India? If you can kind of argue that, then you can generalize.
so if I sign a study where I follow up all children since 3 years after practices, and when I try to find out and the culture of that culture of
That is proportion
So-
of patients developing sepsis.
ma'am, can I tell that in this case, can I tell the incidence of culture positive infections in children?
In our population.
In your population you can, but again, incidence is, I don't know, like when you say new cases is the keyword. I don't know how you assess the new case. I don't know enough about like how you do.
In both type, more or less are sent. I always send. So more or less we get the kinds of hits that we expect with necrotic syndrome. It's more or less generalized into other parts of the country as well. So now if I follow all these children after first 3 years after
Do
diagnosis-
you actually keep a track of when they change from non-disease to disease?
Yes, sir.
You do. Okay, then you can. Because then you can define who are the new cases. And remember, it will change over time. Right? So the incidence of at this point in time was your denominator will be like how many people were risk free before you started this time period. and of those who develop the disease. That's for incidence. For prevalence, you are saying that the number of people with disease divided by the total number of people. That's at that point in time. But for incidence, before you start that time interval, how many people did not live disease free?
How do we get that data? Because this is an institution of issues. I mean,
That's exactly why I am saying that. Like,
in this case, man, the disease is not necrotic syndrome.
the disease is the outcome.
So whenever a child is having a culture positive septicemia, definitely the child will come to the hospital. And
The proportion of patients developing septicemia.
so that is in any case correct. But can I say I am calculating the incidence for 3 years? I am same number of, but that's it. Won't that be the incidence also, madam?
Incidence, so you have assess at every, like, let's say 3 months, 6 months, say, okay, the 3-month incidence, because your denominator has to be the number of patients was that outcome free before the beginning of the interval.
Yes. So, ma'am, that's what I'm saying. This is an acute disease. Any child who is having septicemia, it's an acute disease. And all children with necrotic syndrome, all throughout, irrespective of whether they have already had this infection once or not, will always be at risk for this infection. So, supposing I have 100 kids who are children with necrotic syndrome, obviously coming to me at various times, so my starting point is not the same. But I follow all these children up for 3 years.
Now, they don't know the status of their septicemia.
Necrotic syndrome diagnosis.
Huh?
I'm not talking about the population, ma'am, not the population of children, normal children.
No, you are talking about this, the children with this condition, but
Yes.
your incidence that you are trying to calculate is for the septicemia,
Yes.
right? But I'm saying, when I say you have to know the new cases of septicemia,
Yes.
and the denominator has to be children who don't have septicemia at the start of the interval. How can you get that
Simply, like for example, X number of children with nephrotic syndrome are there, and none of them have septicemia today.
Yes, that part you will need.
And then
you can.
I am following a period of 3 months. At the end of 3 months, I see that Y number of those X children develop septicemia.
So then your denominator
Y
becomes X minus Y
Yes.
at the beginning of the
So
second
then can we
interval.
tell that the incidence of septicemia?
X minus Y.
That's because your denominator has to be people who are free,
From the
who
sepsis.
haven't developed sepsis by then.
So those who
That's
have
the
sepsis
incidence.
divided by those who do not have sepsis.
So,
So that
ma'am,
will
we
be
can see that mistake.
If you can, then you can call it incidence in your population. But what but be very careful. That's the basic fundamental difference between prevalence and incidence. Prevalence is like at any snapshot in time, you are saying X% of the population has been, I mean, for lack of a better word, like X% of the population has septicemia. Who is the population? People who kind of walk in to your clinic. Okay, and you are saying that, some sort of nephrotic condition. Okay, that's prevalence, any snapshot in time. Incidence is, no, I mean, how many new cases of septicemia did I have at a point in time out of the people who were still hadn't have septicemia? So they had to be sort of free.
Here, basically the denominator population who are at risk.
Yeah, at risk to develop septicemia.
Yes.
Yeah,
That is the X.
yeah.
So at the end of the service,
At risk to, when I say at risk means that they still haven't developed septicemia, but they could.
So for incidence, the denominator with the population at risk, and for prevalence, the denominator of whole
Yeah, it can be any big. I understand what you are saying. They eventually for kids who present with nephrotic condition, eventually they will develop septicemia, right? Every kid will probably. But what I'm saying is that for your incidence, your denominator can only be the population that till that point hasn't developed septicemia.
Suppose you get run from what point? What do you consider at that point?
That's study entry.
এটা কনফিউশন হচ্ছে সেদিন আমরা একটা নাম্বার দিয়ে দিলাম 100 জন বাচ্চাকে আমরা ফলো নেফ্রোটিক্স
Yeah.
আর 3 মাসে দেখা গেছে যে 100 জনের মধ্যে 5 জনের সেপ্টিসিমিয়া হয়েছে তাহলে ইনসিডেন্স কি
সেই পয়েন্ট থেকে স্টাডি এন্ট্রি পয়েন্ট থেকে পাওয়া যাচ্ছে না, হ্যাঁ, মানে স্টাডি এন্ট্রিতে যে 100 জনকে
100 জনই ভালো ছিল,
100 জনই ফ্রি তো ছিল। আচ্ছা, এইবার প্রথম টাইম during the first interval the incidence would be 5/100. During the no, I'm not done. During the second interval, if 3 more people develop, the incidence would become 3/95. Yes.
But I want to put a question to Dr. Sinha. So ma'am, so first 3 months it is 5/100. Next 3 months.
And 5/100 upon given that you check whatever biomarker you check for septicemia, at the beginning of the study entry, nobody had septicemia.
For the next 3 months, it was 3/95.
Yeah.
So if I follow up is over next 3 years, still this sepsis, if it has happened to the child, again
New cases. পাঁচজনের তো ওই ইন্টারভেলে হলো, প্রসপেক্টিভলি ওই ইন্টারভেলে হলো। না, তার কারণ হচ্ছে 100 জন শুরু করেছিল। অ্যাকচুয়ালি সত্যি কথা বলতে কি ইনসিডেন্সটা মানে we are for trying to understand we are breaking it up into 3-month intervals. You probably want to do even in shorter interval, right? So the what it is that at the beginning of the study entry, nobody had the disease. That's the key. So they were all at risk of having the disease.
I mean, in this case, I'm sorry, my friend just asking the same question. Suppose I calculate incidence in 3 months over a 1 year. So I have 100 to start with. In the first 3 months, 5 of these children had sepsis. So in the first 3 months, my incidence will be 5/100.
Yeah.
Now in the next 3 months, if I see those who are disease free, now this septicemia is an acute infection, and it has happened to 5 children. Doesn't mean cannot again happen in those 5 children. Yeah. So all those 100 children are still under my control.
No, it can be, but again, it's yeah, it can be, but the thing is that how would you count recurrent infections versus new infections? That's the thing, because recurrent infections are in a way they are correlated events, right? There is a big literature on statistical methods to handle those kind of recurrent. That infection, recurrent infection in the same child has to be treated differently than a new infection in another child.
So if the incidence of recurrent infections.
Yeah, if you are looking at the incidence of recurrent infection, that then the kind of the denominator sort of will remain the same.
I want a similar question to them, they are the nephrology. Suppose if you were to find out the incidence of nephrotic syndrome, it's not
No, that is no. Yeah.
Because so this case incidence, in this case I have the denominator has to be the pediatric population.
Exactly.
Free of nephrotic syndrome. So can we do such study?
If you, I don't know if you have data for that. I mean, do you check for nephrotic conditions? You cannot do it at the population level, period. Because who goes and check like, I mean, in a normal child, if they don't have any symptoms, you wouldn't put them to a bunch of tests, right? So at the population level, you cannot.
So those need to be collaborative or maybe counter
Yeah,
studies.
yeah. So typically in studies like that, you would report like prevalence. The prevalence of, like for example, beta thalassemia is a very prevalent disease, right? In India, the little I know. I mean, in order to calculate true incidence, you have to know the population. But I don't know, is it possible to kind of know? So what you estimate is the prevalence. Any snapshot in time? And studies report the prevalence of beta thalassemia in India is X times higher than other countries.
Can that be a single sentence? And I do a preference just in my
You can, I see it is probably, you can argue it's very representative of India's pediatric population. I'm making it up. Yeah. So there, yes, you can.
And what is my denominator?
The denominator is your hospital population, but you cannot get population based estimates.
When I say my hospital, I need to have an idea about all the patients who are visiting ICH regarding that particular disease that I'm
Yeah. Yeah. So, okay. So I probably lost a few patients. Sorry, not patients. Lost a few people from the audience. Prospective cohort study is basically the study begins at the time of where you have cases and you have controls. You have cancer patients and you have non-cancer patients or healthy controls, and you follow them over time. So basically, the study information is obtained prospectively, and your outcome is again, it depends on. For example, let's say you are looking at mortality, overall survival. So that is a prospective study. Oftentimes, prospective studies are also like essentially like you take a bunch of cancer patients, you follow them over time, how many recur, you catch recurrence, you catch their, and it's again these are prohibitively expensive studies because you are following up patients. So the United States has many large longitudinal cohort studies through the national health statistics. So the Baltimore longitudinal study of aging is a classic example. They have I don't know 40-50 years worth of data on social factors, disease factors, lifestyle factors, but these are typically kind of born out of a lot of federal funding, multiple institutions together joining a consortium. And so these are really long-term follow-up cohort studies, extremely rich. I mean, so many people have gotten their PhDs out of like the Baltimore longitudinal study of aging because there is so much data, so many things to study. But again, these are generally the cohort designs are sort of the, how do I say, the hallmark for like great study design, but the problem is they're very expensive. So these are best for relatively common diseases where outcomes happen quickly, right? Or diagnosis happens quickly, rare exposures, and then the concerns are, loss to follow up, attrition, missing data, confounding by indication. So lots of kind of, from a analytic point of view, nightmarish issues. So here is an example of a cohort study of British doctors who were followed for 10 years, and the exposure was cigarette smoked per day at the start of the study, and they were followed up for 10 years. On the farthest column on the right, we have the annual death rate from lung cancer per 100,000 people in each of the groups. So here you can sort of estimate the long-term risk of developing lung cancer was 32 times greater for the heavy smokers compared to the non-smokers, right? So basically this is okay here, and we were having all of this discussion in the morning. Here you can estimate risk ratio, relative risk, okay, because you are prospectively collecting the information. So now here the risk ratio is for the heavy smokers who smoke 25 plus cigarettes in a day, was the annual death rate was 227, and for the non-smokers is 7. So 227 over 7, that's the relative risk or the risk ratio. So this is the point that I was making. Like for cohort studies, you can estimate relative risk or risk ratio. So here, as we see that the risk of lung cancer was 32 times higher for heavy smokers compared to non-smokers. Experimental studies, I am going to just briefly talk about randomized clinical trials. Looks like not too many people here do RCTs. Do you guys do RCT? A little bit? Okay. So these are AKFA studies, and just to be fair, because I don't do RCTs much, I mostly work in the observational studies arena. Because statistically, I feel they are much more exciting, challenging. There are so many difficulties, issues. But there is also like a big literature on randomized controlled trials, statistical methods and design. And there are many phases, as you know, of RCTs. Starts
from the
the
vaccine study, we only randomized.
Yes.
Do a lot.
Yes. I'm saying from a statistical perspective, I find observational studies much more exciting, challenging, because there are very, like, how do I say, tricky analytic issues. Randomized trials are great for evidence. They're gold standard, right? But randomized studies, because you can allocate the treatment, you can make the level the playing field between the treatment group and the control group, because by balancing, by stratification, by doing randomization certain way, that you are making the treatment and the control group kind of quote unquote what we say similar based on other factors. And there are various things that you can do at the design phase. So what that ensures is when you are comparing the outcome between the two groups, you are saying that, you know, everything else, because they're same between the two groups, the impact that we are seeing, the difference we are seeing is due to treatment. So it buys you that. Whereas in observational studies, you can't. It is what it is. And so it's harder to analyze, to model, because it can be quite tricky. So firstly, it has to be randomized, have to have unbiased assignment of treatments to participants, controlled. Internally, you are assigning a contemporaneous comparison group. That's who are my controls. And as I said, the experimental and the control group has to be comparable with respect to other factors like age, gender, might be sort of have an impact on AKI, right? And suppose you are trying to compare two drugs, so you randomly allocate the drugs to a group of patients, but you try to equalize the playing field between the drug A versus the drug B group. And one way you can do that is you do stratified randomization. If you think age and gender are important, then you randomize within males, within females separately. You randomize within age groups so that you have a balance in age and gender for the experimental versus the control. And then the blinded aspect, double blinding, neither the participant nor the investigator knows which intervention the participant received, which allows us to make an unbiased assessment of the effects. So blinding, as you all know, there's a placebo effect that many studies have shown. So this is a way to ensure that there's placebo control, but at the same time, there is no biased assessment of the effects.
Now, one question. Now, in the vaccine study, first, who is the vaccinator? He or she will know the vaccine is given. So, this is not actually, it's a double-blinded study, but the person who is administering the vaccine, only she or she knows what is given. So, what is this study?
No, it is still randomized. It is
randomized, double-blinded. It could be double-blinded or because all the investigators are blinded. Only one investigator who is administering.
It's actually not. The person who gives the vaccine is not the investigator. He or she is putting the vaccine.
No, investigator.
The vaccine.
Yes.
No.
Investigator will be administrator.
No.
Yes.
Really?
Yes, I agree. I am one of the investigator and we only administer. Because the administration will be done by the one of the investigators.
For COVID vaccine?
Not the COVID. We do lot of studies on the vaccination.
No, I mean, typically
vaccination of the children, starting from the 6 weeks to 10 years old.
Yeah, no, typically like double-blinded is sort of how do I say, the old standard. I mean, you at least in the US, I know you are held very strictly, and the way you are blinded is the person who is giving the vaccine might know, but the person, when you ship the data to the person who is analyzing, that person has to be at least, but generally, like investigators.
It can be called double-blinded study?
No, it won't be double-blinded, but it would be blinded to the analyst. And again, as I said, in US, the standards are held very strictly. That's why I was a bit surprised. As an investigator, you wouldn't give the vaccine.
So that's why when we analysis with SARS, it come up as a bias.
Yes. Yeah. Yes. So the blinding is kind of broken. So again, I don't know. There are different ethical codes, ethical standards that different countries follow, but generally, that's the standard. That's the norm. For example, if you are the principal investigator of the study, you don't see the data unblinded. You are assigned
not the principal investigator. Suppose I am the co-investigator, I am administrating. Principal investigator is blinded. Everyone is blinded. There may be 3 or 4 investigators. One is principal investigator. So
I mean, as long as
assigned to administer the vaccine.
Yeah, it's not about I mean, it's kind of. I'm going back to Shakespeare. What's in a name? A rose will smell. So what's in a name? Like I wouldn't call it. I may call it blinded. I may not call it blinded. The bottom line is somebody who knows about who got and who did not get shouldn't be even touching the data. Bottom line, because that's where the bias will come in.
If that person is not touching the data.
Yeah, so
only
but
administering, and only in the double-blinded group, that is the only person who knows about the vaccine.
yeah, so
Nobody
that's
else.
so
Even the who is getting the beneficiaries, not other investigators, not the sponsors, or the company which is sponsoring the who's under whose sponsorship doing this study. Nobody is doing that. Only the person, because the label will be there in the vaccine. So he or she will. Because if there is some sort of labeling other than the vaccine, then only it will be a proper document.
yeah, no, but I mean that's why I said Shakespearean. What's in a name? If you want to call it blinded, yes, as long as you have no input in the data analysis, number one. Number two, you don't even see the results. So that's why I am a bit surprised. Typically, an investigator doesn't administer the treatment.
Now, let me explain this. What happens is that under the principal investigator, you have certain co-investigators who have been assigned with certain jobs regarding the clinical trial. So if someone would have to administer, a doctor would have to administer who is also a co-investigator, then that co-investigator is assigned to do that administration. But he or she should not lend out the details to anyone else.
Yeah, so like so in a way you are again I'm just like I said, there may be different ethical standards different across countries, but typically in the US, like investigators will not administer the treatment, the vaccine, and secondly, the person who will administer the vaccine, when he or she ships the data to the investigative team, it's totally blind.
Because somebody else is doing the
Somebody else is. Yeah.
So
So that's
outside the trial is doing.
yeah. That's the thing. So like again, name wise, I don't.
So basically, sometimes in journals, they ask for each investigation.
Yes, exactly.
So as I said, it's investigation of administration of vaccines. There itself, the question of
Exactly. Yeah, and that's what I am used to.
There are many studies where they ask for the investigator only to administer. They are doing a lot of studies.
Yeah, so again,
they have a data protection by which the results
because
come from the
data confidentiality is a huge thing in the I mean I think in most countries that's a huge thing. So in fact,
whether that can be still called the double-blinded.
and that's why I'm saying give it any name. What's in a name? Because I it's like my issue is again the data confidentiality issue, and yeah. So for example, when we get data, let's say there is no, so if all of us involved in clinical research at the institutional level, I am sure here also you have to do IRB, right? You have IRB. So the IRB is going to like question, make a lot of noise if a data comes to me in some way where I can link it back to the patient. So much so that if there are like certain very small groups of patients that with one or two identifiers I can link back, they're going to suppress that data. So it's that stringent. So that's why, and it might be different. Okay, so the goal in the reason why clinical trials are sort of the gold standard is because you are reducing bias and variability, and by essentially bias is reduced where any influence which acts to make the observed results non-representative of the true effects of therapy of vaccine, we have sort of reduced that by making the two groups sort of as similar, right? And again, this is like really a very broad overview. There are so many nuances. Um, and variability is the imprecision in estimates caused by sampling from non-population with tiny sample size, which is basically what we have to do in observational studies, right? There's so much of confounding. So clinical trials kind of reduce both bias and variability, which is essentially why RCTs are hailed as the gold standard of any drug study. Treatment A tests better than B, so more of A actually swallowed. Bias arises from things like this. Healthy patients were given treatment A, sicker ones were given treatment B. So these kind of things you can control by random assignment in an RCT. Which
I have a question on this. Suppose in a cohort study you cannot control. I just saw one of his slides with age match.
Yeah.
How do you do this? Suppose if it doesn't, your case and controls show difference in age or gender, then how do you, I mean, very
No. That's why you do the regression adjustment. Yeah, that's why. And then there are other methods to adjust. For example, how many of you have heard about propensity score matching? Okay. Yeah, so propensity score matching is a very sort of a new cutting, well, not cutting edge anymore. Everybody does propensity score nowadays. But propensity score is trying to mimic what would happen in a clinical trial if you could do that in an observational study. So it's often called a quasi-randomization technique. Because in observational studies, you cannot randomize. So quasi-randomization techniques where, say you have a variable that, this example, healthy patients were given treatment A, sicker patients given treatment B. It so happened that in observational study, that's what came out. So how do you compare? Like, because the patients who are healthy are going to do better. So it's not because of treatment A, but it's because they were healthy. So that's where propensity score comes to use, because then what you are trying to do, you are trying to balance treatment A, treatment B based on the health status of the patient. So it's a quasi-randomization. So you would adjust. You would do propensity score. There is also another approach called the instrumental variable approach. Which is again, all of these techniques are trying to mimic what would happen in an RCT if you could sort of do that observation.
I don't know whether I'll get the opportunity anywhere else like to clarify this. But when I heard first about propensity score matching, someone told me that something the approach has come which converts non-randomized trials into randomized trials. I guess how can this happen? So then I did a beat and found they are comparing things one by one in that manner. So that I understand much, but I understood something, I think. And then in my like postdoctoral exam, in case here I did, in my theory paper, the question came reverse propensity score analysis. I had read propensity score analysis, I scratched my head, what is reverse propensity score? And I left that question. So what is that?
Okay, so the reverse propensity score, I mean the inverse probability weighted, that's again, I'll just say it at this point because it's what? It's 440. You don't want me to write any like ugly mathematics on the whiteboard. It's essentially another way of like a quasi-randomization way. And it tries to upweight, give more weight to patients for whom or for variables that have a different kind of balance between treatment group A and treatment B. So it's again trying to mimic what would happen in a RCT, but by cleverly incorporating weights, cleverly incorporating propensity. So the propensity score analysis gives you a set of, let me try and give you a bit more detail. The propensity score analysis gives you a bunch of propensity, right? Propensity is a likelihood. It's a likelihood. So what's the likelihood of being healthy or sick? And you kind of balance the treatment groups in terms of that propensity. ITW is essentially taking those propensities and using them, incorporating them as weights now. So, yeah, these are I mean, conceptually again, these are not really hard to understand if explained in the right way, but also simple concepts, because you are saying, well, if you are giving treatment A to healthy patients and treatment B to sicker patients, it just turns out that way. The outcome difference is not due to treatment A versus B. It's primarily between healthy versus sick. So how do you balance it? That's the idea. Variability, I think we can sort of skip this. I like to show this picture. Did you take the
Yes.
Okay. So I will end with this slide. Sorry. I 4:45. I like to show this picture because bias and variability are two very important concepts in statistics, and we are always trying to get unbiased estimation and least variable or most precise estimation. So if you think of like a dirt board, and you have the bullseye, that inner circle, and you are throwing darts. Your objective is to hit that inner circle. So let's start from the very your right side. So 3 tries, all kind of the same area. All 3 times you have missed the center. So it's a bias estimate, but it's precise because the variability is very little. All 3 times you are at each other. The middle picture is the worst because 3 tries you are all over the place. You never hit the bullseye. So this is an example of unbiased. It's an example of unbiased but imprecise. Unbiased why? Because statisticians love average. On an average, you are in the bullseye, but it's like a confidence interval which is very wide, right? You have got it, but you are so variable that you will have very little confidence in your results. And here on the leftmost is you have hit the bullseye all 3 times in the center, and you have hit the target right. So this is an example of precise and unbiased. Ideally, you like to be here. And that's sort of the effort that we spend. That's why, and as a closing note, days of your life gone trying to get precise and unbiased. Okay, so thank you all for being here. And should I sort of close the Zoom
Stop share.
and leave the Zoom room, or what? Should we do a few certificates?
Yes.
Yeah. Do you need the URL now or no?
We have circulated it in the, and some who have joined through Zoom we will send it to them. on their mail.
Okay.
So those responses will be coming a little late, within 24 or 48.
Okay, so I didn't get a chance to sign. I'll sign a few now. And over here.
Our certificate. And here. Can you put in the names of people who are there in the audience?
Yeah.
And that is when আমরা নিচ্ছি collection actually করে। আমার নাম ডক্টর রিনা ঘোষ।
Dr. Reena Ghosh. Kiran,